All right, we're going to get started. So good morning, everyone. I am Gabe Margolis, and I'm going to be delivering some welcoming remarks to this workshop on sim-to-real robot learning for locomotion and beyond. So why do we want to use sim-to-real? I think the past few years have demonstrated that there are a lot of benefits of learning, but there are also many challenges of collecting data in the real world. And so sim-to-real learning is an exciting paradigm to sort of bridge the gap between these two realms. And in recent years, there's been some exciting progress, robots that stand up, manipulate things, but there are many remaining challenges. So in this workshop, I hope that we'll be able to sort of explore together those challenges and come to a better understanding of how to address them. So I just want to go over the schedule for the day. So we're starting right now with the welcoming remarks. Following this, we'll have our sim-to-real tutorial. And actually, I'll go through each thing individually. The important thing to note is sort of the first part of the day will take place in this room, and the last part of the day will take place in this room. In the middle of the day, we'll have our poster session and our demos, which will take place actually in this building, but right outside. The posters will be on the 4th floor where you entered through those doors, and the demos will be down on the 3rd floor. Just take the stairs right down. Yes, so to go through the schedule in a bit more detail, we'll start in just a moment with our sim-to-real tutorial, which should be an exciting look at some very recent work in this area. Following that, we'll sort of have 2 blocks of really exciting speakers who are working on sort of different aspects of sim-to-real and application to different robotic systems. And of course, we'll be introducing each one when it comes time for them to speak. And of course, we'll have our posters, spotlights, and demos, which we're excited to host. So we received a number of exciting contributions, and you'll be able to see the demonstrations just after the sim-to-real tutorial during the spotlight demonstration block. We'll have 3 demonstrations, and then we'll have a few lightning talks by some authors of the posters. Then later in the afternoon, after lunch, we'll actually have the poster session and just demos that you can come up and interact with. And those will be running, as previously mentioned, sort of outside on the 3rd and 4th floor. And then finally, at 3:15, we'll have our spotlight presentations, which will be more in-depth talks from a few of the poster authors. And to conclude the day, we'll have our panel discussion, which should be an exciting time from 4:30 to 5:30, where the panelists will sort of debate different aspects of sim-to-real. So yeah, that is our schedule and day. So with that said, I will hand it over to Pulkit and Deepak for the sim-to-real tutorial.
Good morning, everyone. Thanks for coming. And we'll get started with an overview of some of the recent advances in sim-to-real learning. I am Pulkit, and along with Deepak, we'll be delivering this tutorial. So we'll try to make this very specific to robotics, although sim-to-real has application beyond robotics also. So let's maybe start with a dream that many of us roboticists have, which is we want a robot, and we could say things like make me dinner, and the robot goes and makes us dinner. Now doing this requires us to interpret. Oh. But am I audible on Zoom? Oops. Okay, right. So now if we consider this task of, say making me dinner, then first thing, we want to understand a robot needs to get is what does dinner actually mean? right? Dinner means there's some particular food items that need to be mixed together. And this is the part of interpreting language and having some kind of common sense knowledge, right? Then the next part is, given that we know what we are making, what is the plan for making dinner? Maybe fruits are or vegetables are in the fridge. I need to get them. Then I need to get my knife, chop things, and put them together. So once we know what is it that we are making, we need to find a sequence of steps, right? But now if we say, hey, I have to chop vegetables, then I actually need to go and execute, these steps to actually chop these vegetables, which is what we are calling as low-level skills. So I think in the recent, year and maybe couple of years, we have seen a lot of impressive progress in going from these abstract instructions to detailed plans. So here is a video from Google Brain, put out earlier this year, in which the robot is given some instruction. I spilled Coke on the table. How would you throw it away? And bring me something to help clean, right? This is what the instruction is. And this is the robot in operation. So it goes, it picks up the Coke can, and then it needs to, says, I picked it up. I have to go it, to the trash can. And then it tries to throw it to the trash can, but it fails to actually put it in the trash can. Then, it goes to find a sponge. So all these numbers, like the steps that you're seeing, the model is getting these steps by leveraging, GPT-3 or similar large language models. Right. So what we are seeing is that we can make these, plans, but executing these plans, still remains challenging. Right. So this is exciting to see how much progress we have made, right, to get to these plans. But the next question is, how do we actually execute them in a reliable fashion? Right. So many people in AI have thought about, this problem, right? And there has been a belief in the AI community, at least some people believe, that things like reasoning, require very little computation, in the sense that making the high-level plan, might be much easier than actually doing the sensory motor skills. Or, put in other terms by Steven Pinker, the main lesson of 35 years of AI research is that hard problems are easy and easy problems are hard. What does this mean is, things like, opening a door, walking on stairs, walking on flat ground, things we don't even think about. Our robots have a very hard time doing those things, right? And, other things, which we think a lot about, what I'm having for dinner, right? Maybe these things, we can get today and do them, really well, right? And this has been known as the Moravec's paradox, right? So, if we go by the Moravec's paradox, maybe, what is really hard is to do the low-level skills, right? And maybe, and then there are other, hard problems which are there, but, what, is really preventing robots from executing things is the inability to perform the low-level actions. Right? So this Moravec's paradox got stated 35 years ago in 1988. And today is 2023 almost. So it's almost 35 years since this paradox was stated, right? And still, we are stuck with the problem of learning robust sensory motor skills. But the question really is, if we have to look forward, what happens, right? So if we look at the past 35 years, we have made a lot of impressive progress in low-level skills, right? I'm just showing you some examples. Right? But, as I mentioned before, probably many of you have seen this video, something is still not working, right? I mean, robots are failing at these very, very, simple things. So, what is it that we need to do so that, if we were to come back and have a CoRL 35 years from now in Auckland, we don't repeat the same thing, that these low-level skills are hard, right? So how does the road forward look like? And feel free to interrupt me, ask me questions if you have comments, if I'm saying something controversial, maybe I'm a bit controversial on purpose. So feel free to raise your hand, ask me a question. Right. So let's think about doing specific things, right? Specific sensory motor things, right? Using tools to chop vegetables, right? So to summarize, if we want to build this robot, we have pretty much used all the data on the internet to make plans, and these plans are working very well. The question is, what do we do about low-level skills? How do we actually get here, right? So one thing, say, hey, why don't we collect data from the internet? Why not give demonstrations? I think demonstrations are a viable approach, but they are tedious to give. But there can be other things, right, which make low-level control really hard, right? So if we just consider a task, which is opening a door, this takes 3 seconds. And suppose this is the control frequency we're operating at, 25 hertz. We have around 30 muscles in our hand. So if you do the math, the search space is humongous, right? So if you were to give demonstration, you have to give lots and lots of demonstrations, before this works, right? And just to put this in context, it's more than number of atoms in the universe. Okay, then the point being, we require lots of data. Where do we go? We go to the internet, right? But this is what we have on the internet is a lot of videos of humans doing things. But there are many challenges which prevent us from leveraging this data. Right? So the one challenge is that many times the morphology of a human and the robot could be very different. The way I move my hand might be very different from the way the robot can move its hand. But I think, more importantly, there is just, there is no data of how to do the low-level skills, right? For example, I could say I need to open a doorknob and I need to move my hand in a particular way. But what about the forces that are being applied, right? What about if my hand slips? How do I adjust back, right? Those things are not in videos. We don't write this information on the internet or even in books, right? So this data is simply not available, right? So we can't really get this information from any large repository that exists. So, what do we do in this scenario, right? So we need to pretty much generate our own data to be able to solve these tasks. Right? But, if we try to, collect all of this data in the real world, this is going to be very expensive, right? In terms of the amount of time that we are going to be spending. Right? And, it is not just that we require lots of data, but if we were to do, say, reinforcement learning, which is generating data in the real world, the other problems one runs into, right? For example, how do we measure rewards in the real world? That is unclear. Then the policies that we end up learning are very specific to one particular task. And, then there are issues of safety when we are collecting this data. Right? So, to summarize, great progress in getting to plans. Low level remains hard, but we really don't know where to get this data, right? And training in the real world seems to be quite challenging. Right? So what do we do? Right? Now, this is where, one route is to use simulation, right? And really train policies in simulation and then try to transfer them in the real world, right? And, really, why simulation? Because we can collect tons of data very quickly, right? I'm showing you this video from ISAC Gym that NVIDIA released. In 3 hours, we can collect 100 days worth of experience. So it's really the scaling laws are in our favor if you were to use simulation, right? So I think it's, it's important to understand, why even consider simulation in the first place, right? It's not that, just because we want to use simulation, we're using simulation. There is a problem that how do we collect data, right? And that is why we want to use simulation, right? So how does learning in simulation looks like? We have some state. Then we assume access to a simulator. What is a simulator? Given a state and the action, it tells what is happening next. And then, based on the simulation, we can leverage different techniques. For today's purpose, we're going to stick on learning-based techniques, in particular reinforcement learning to learn a policy pi. A policy maps, states to actions. And once we have this policy, we're going to deploy this policy in the real world. Right? So that's the training in simulation going to the real world. Right? Everyone with me? Great. Right? Now, what's the first thing? Right? If this paradigm has to be successful, what is the thing that we need? Right? The first thing we need is the simulation. Right? How do I get the simulation? Right? Now, it turns out that for some things, for example, if I have rigid bodies, we can do very fast simulation, and things are good. But for other things, we know the physics, but it's really hard to simulate. Things like cloths and ropes and all the deformable and soft materials. Or if you're working on physics problems, right? I mean, there are tons of things which we know, like we can write down the equations, but to simulate them is very expensive. Right now, this is a concern because if we are going to use simulations to collect large amounts of data and the simulation is slow, that's going to be a problem. Right? And the third thing is, there can be some scenarios where no analytical models exist. For example, if my robot has to interact with a human, I need a model of a human. But how I cannot write down in math, what is a model of a human? I could have to estimate it from data, but the point being that there is no mathematical equation that is principled to simulate humans, right? So I think, so in general, for some things we can build simulators. For other things, how to build simulators, remains an interesting open research question, which we will, dabble a little bit in the end. But for now, let's focus on where simulation is actually possible, and we can do fast simulation. What happens in that context? Any questions, comments? Nope. Okay. Right. So then we can say, hey, if I have fast simulation, are things going to work out? Right. The answer is, not quite yet. And why? Not quite. Okay. Okay. I mean, why is that? Suppose in simulation, I need to set, some parameters. For example, I need to say, what is the friction between the foot of a robot and the ground, right? I need to say how heavy is the robot, right? Now, there could be some misspecification. For example, I might train with high friction, but then if I have icy snow, the friction can be low. So there can be misspecification of the parameters that we set in simulation and the parameters in the real world. Right? Somehow we need to overcome this. Then there are things which are hard to simulate. Things like sand or gravel, right? Like this goes into the second category where if you have a rigid body simulator, and then you have to simulate lots and lots of rigid bodies, typically you don't do it because it becomes extremely slow to do that. Right? And sometimes, not only can you not simulate things, but somehow your sensing can make the robot be limited. For example, suppose I have a quadruped which has a depth camera on it. Right? So if I observe this glass from a depth camera, this glass would appear as solid. Right? Because depth doesn't tell me if something is pliable or not. It will just tell me this is an obstacle or not an obstacle. So now if I see grassy terrain, the robot can walk on it because if I put my step on the grass bends. But if I just have a depth camera, it is not obvious that I have that information from it. Right? So sometimes, on the real hardware, we don't have the sensing capabilities to measure some properties that we need to measure to be able to deploy a policy. Right? So you can kind of break down the reasons why training in simulation and transferring to the real world is hard in these three major chunks. Does it make sense, what I said? Right? So now, among these things, we're going to look at the first part, which is model misspecification, and see how do we deal with it, and then go to some other parts later on. So, let's try to pose this problem more concretely. Suppose I have my state ST and I'm trying to learn a policy pi, which produces action Z. Right? Typically, we have some reward function. So the reward function is how fast my robot is running. And suppose I just want to have a robot which runs, right? And now what we do is we set some simulation parameters, right? And what do I mean? I set some friction coefficient, the mass of the robot, so on and so forth, right? Now, what I can do is, I trained with this simulation parameters, I get a policy. And then we can go on and deploy this policy and see its performance. Right? So what I'm showing over here is that if I am measuring performance at a friction of 0.5, the robot is doing well. But as I have a different friction in the real world than what I trained for, the performance drops. Right? And the reason this happens is because there's a misspecification in the parameters, between what I trained for in simulation and what happens in the real world. Everyone with me? So this is the model misspecification problem we just discussed. Now, how about, we go about fixing it, right? So here is where this idea of domain randomization has been used quite a lot, which says, suppose if I want to, deploy a policy on the real world to say stack these objects, right? But I don't know what are the parameters in the real world. What I'm going to do is in simulation, I'm going to take many, many different settings of those parameters and try to train a policy which works across all of those settings. Right? So for example, over here, we can train policies which have seen many, many different visuals and mass and the friction of these blocks, and have that policy work across all of those parameters and then deploy it on the testing scenario. Right? Now, to put it mathematically, we have these parameters D, and we're going to find a policy which is robust to this choice. Right? So for example, now what I'm going to do is I'm going to have a range of these parameters, which I believe is reasonable. So 0.05 to 4 is where I vary my friction, motor strength, so on and so forth. Right? And if we train the policy in this particular way, this is known as domain randomization. Now, if we look at the performance of the domain randomized policy, which is shown in red, what you see is, it seems to be performing, better than the nominal policy, right? Because I've randomized the ranges. Right? But, as a designer who is building the simulation environment, one question which comes up is, how do we get these ranges? How do I set how much the friction should be, how much the mass should be, so on and so forth? Typically I would have some intuition and I would set it. But, this could be suboptimal for, many reasons, which you'll get into, right? So the other idea which has been explored is to do automatic domain randomization, where we try to automatically find these parameters, right? What is the range of the mass? What is the range of the friction? So on and so forth, right? But the one issue which can happen is that we can set infeasible parameters if I'm automatically trying to find what is good. For example, what if I set friction to be 0? Right? I mean, there's no walking which is possible on friction with 0. Right? Or I might command the robot to go at a very high velocity, which is not possible given how much the motor strength actually is. So if I'm doing domain randomization, and if I'm not careful in how I set my parameters, most of my domains might not even have a solution. What that would mean is that I almost never get a reward. And if I don't get a reward, my training is not going to work at all. Right? And that is really the challenge which comes in when you're trying to automatically design a curriculum. Yes.
Isn't it really challenging that you of these ranges, train a bit, and then automatically deploy a real robot, and then this goes, this takes too much time.
Yes, so it's like unclear. I mean, how do you evaluate if your automatic range is good or not, right? That's the point you are trying to level. Yes, which is a problem, right? But suppose suppose somehow yeah, we'll come to it. We'll come to it, right? But suppose somehow we can set these parameters, and some works have successfully done it. Then we can get policies that are, able to work, right? This is, a paper, for quadruped locomotion, training policies in simulation, and then, really deploying them in different conditions in the real world, leveraging this, domain randomization as an idea. But the one thing, this work, also makes note of. Oh, I think, Deepak, you have those slides. Okay. Okay. So, okay, I'll transition it to Deepak, and then he can, discuss. So, yeah.
So you can stop sharing your screen.
Yeah, so what I was going to say is, if you do domain randomization, then you get a performance hit, in the sense that you become conservative. And imagine if I said, walk no matter what the friction is, right? Which means that I have to walk on ice, I have to walk on very slippery surfaces, and I have to also walk on glass. What would I do in that situation? Maybe what I'll do is I'll move like this, right? Because if I move like this, which is very conservatively, I'm not going to fall everywhere, right? So doing domain randomization can result in, conservative policies, right? So it's almost, there's a trade-off between robustness and performance. And, this is what Deepak is going to talk about, how do we bridge this gap between robustness and performance, so that it's not really a trade-off, but we can try to get both of them.
Yeah, I think we need to, okay, we have exited the Zoom. Okay. There's nothing to join, right? Speaker on there. Yeah, but nothing to speaker. Yeah, no speaker. Yes, shut it. Okay. Okay. Okay, hi everyone, I'm Deepak, and so Pulkit showed this cool work on randomization, and turns out the first author of this paper is sitting right in front of us. G is here. So this is very cool, and there are other examples of randomization like Pulkit explained earlier. And many things are randomized in all this. Like you randomize not just appearance, you randomize dynamics, you randomize friction, and all these parameters. Now, on the surface, these results look very impressive and very good. And turns out this problem is very easy. But if you go to the appendix and you check out the parameters, this is what it looks like. Like this is the appendix of the OpenAI hand paper, and this is one page of 15 pages of appendix as to what all they randomized and what are the ranges they pick. This is not days, but weeks and months of tuning on the parameters of these things. And I could not take a snapshot of the whole thing. This is just 1% of the whole appendix, or 10% of the whole appendix which is there, right? So this is, and you randomize all these parameters. Now, this is a challenge for engineering, because of work. But then there is other issue that doing this also trades performance, and Pulkit explained this towards the end. Then here is this result from G's paper, where they show that if you do not randomize, you can get to good return at some point. But if you randomize, the performance is usually lower than what would be the case when you don't randomize. Okay. Now, this is not very surprising, because when you're randomizing, you are trying to make sure the same policy works across many scenarios. Like if you were asked to walk on ice as well as on carpet without knowing what they are, you will walk very conservatively. And this is what causes the performance drop. Then maybe one solution to this problem is better system identification. Like if you could identify the system better, like which environment you are in, you could probably perhaps adapt your scenarios. And this would lead to less randomization, because you don't have to worry about all possible terrains. You can identify where you are and act in that scenario. But usually, like systematic is a very old area in controls. This goes back to 60s and 70s, where people identify the parameters which drive the environment. Like you are flying aeroplanes or planes at very high speed. What is the wind turbulence and all these conditions? And you have to identify all those parameters. But in a higher dimensional setting, and this is very tedious and very slow, especially when the environment is present out there, which is changing very rapidly. Like flying in the air, there is still free body across, like with no obstacles to hit no contacts out there. But on ground or doing manipulation, you have contacts every few milliseconds, which you have to worry about and reason about. So the question is, can we somehow automatically learn the system ID while acting in the real world? Okay, so this is the line of work which is still pretty much an open problem, and there are some interesting works out there, but this is by no means a solved scenario. So let's say you are learning a policy in a simulator. So when you have a simulator, you have to set up parameters of simulator, like what is the friction and what is the basic, even something as basic as simulation frequency, at which rates are your steps being taken. Usually when we use simulators, we hope that the person who designed it has taken care of all these issues, but somebody has to do it at a certain point. So let's say you have some sim parameters that you have to tune. Now you do have to list all the parameters which you need. So let's call this vector psi, and this can include parameters like friction, restitution, weight, and all these scenarios. And then you have a control policy which you are learning, which then you will execute in the real world. Now, the question is, unless you have already pre-engineered the system, you do not know what ranges of parameters should I set in simulation for them to truly reflect what it should be in the real world. I can randomize the ranges, but to randomize the ranges, I need some lower and upper bound, which needs to be roughly right with respect to the simulator. So there are work in the community which try to somehow use data from the real world and go back to simulation and adapt those ranges in an online manner. So you use data from the real world and incorporate that back into tuning of simulator. Okay, so this is one example of this paper from NVIDIA, where they have the simulation that they are building. Again, ISIS, and you have real world deployment of the same robot. And you start with some sim parameters, let's say some ranges for friction or some ranges for restitution. And then what you do is you execute your policy, which you learned in simulation, in the real world. You collect the trajectories, and then you see what those trajectories are in simulation and real. So you try to map the real world trajectory and find the error with the same rollout in simulation from the same starting point. And then you use that difference in the real and sim trajectory to update the parameters of the simulation. So you backprop the error, which you get by comparing real world trajectories to sim trajectories, and you update sim parameters from that. Now, in this situation, I believe they use gradient-free method. They don't use gradients to optimize, but they use cross-entropy method to update the parameters of simulation. Now, this, of course, tarnishes the picture a little bit, because now real world is involved as inside the loop of training the policy. So this becomes slow. So you can still do 99% of training in simulation, but then you have to still go to the world and update the simulator and repeat the training again and again over time. This is one problem. But the major problem is, how do I do such a thing for the environment? Now I can easily observe how my robot is moving, what my angles are, what my velocity is of the joint of the motors. I can see the trajectory, but let's say if I move an object on the table like this laptop, how do I exactly know how much force I applied and how much the laptop moved? I can know this in simulation, but it's very hard to know in the real world. So you need to track every object in the real world to very precise accuracy, which again is a non-trivial problem, and perhaps not the right way to go about things, because I cannot, like, what do I even measure? Like if I blow some air and somebody's hair move, do I measure how much their hair move in simulation and real and compare it? So this becomes very difficult as soon as the environment is involved. So these methods are used pretty much for the robots, but very hard to scale to environment. And this is one of the open problems in this area as to how to automatically tune simulator when the environment is involved in the surroundings. Okay, so now suppose this environmental simulation is not there. Let's say we are in a setting where we know some finite number of parameters like friction, restitution, weight, etc. Can we somehow still estimate these parameters online while acting in the real world? Okay. So now, unlike before, we are not writing this policy to be invariant to all the parameters. Now, this policy is conditioned on parameters D, which come from the simulation. Okay. So this is privileged data because in simulation you have access to mass, friction, etc. You can train policy conditioned on that. So this is saying your policy is now aware of the surroundings and is not invariant to every situation out there. And then you can try to learn this policy using reinforcement learning inside the simulation. Okay, this is your policy. Now, in this situation already, you start to gain something. So this orange curve is a normal curve when you don't have randomization. Red curve is the one when you have randomization. So performance is slightly lower. But as soon as you add this information about the environment, this is the blue curve, which is the highest performance. Because now policy is not trying to find the same solution across every setting. It is trying to adapt and condition on those settings. But the problem is you cannot deploy this because it's not available. Okay. So one variation of system ID from controls literature is to try to estimate these parameters online from the data which is available on the robot, like history of the robot. So for instance, at test time, if you can somehow estimate this D vector, which contains friction, mass, etc., on the robot itself, then probably you can deploy it. Okay. So, so this approach is called online system ID, or in other words, explicitly trying to estimate the parameters of the system you are training your policy in. So you are trying to estimate all the parameters like friction, etc., online from history of the robot. Okay, so this history of the robot, ST minus S to T minus 1 to T minus H, all this history is taken as input, and you learn the parameters of simulation. Like for instance, in the real world, like if you, for some reason I'm hearing my own echo back. Let me check this a little bit. Select a speaker. Okay, so we'll see what happens. Okay, so you can estimate the parameters like friction, mass, etc. from the history of the robot. So you can look at what is being commanded and what is being happening on the robot. Now this is a very challenging problem. Like for instance, do I really know what is the friction of this carpet when I walk on it? Like, is it 0.5, 0.6, or what is the value of friction even mean to me? It's a very hard problem. But nevertheless, we have seen some interesting results to this approach. So here is a paper from Jiming, and here they are making this robot run very fast on this on the roads, on streets, and this paper is purely from this approach of explicit parameter estimation from the history of the robot. So they estimate all these parameters which are required to be updated in the real world at test time. Is there a sound that you heard? No? Okay. I don't even know if this is a sound. Okay, so so they have very good results from this approach, but in general, this is very hard to obtain all these parameters. Now there is one more problem. For instance, there may be coupling between the parameters. Like if I have a heavy object and I slide it, if it does not slide, how do I know whether it is not sliding because of high friction or high weight? Now both of those things can lead to similar outcomes in the observation history. So it's very difficult to realize or how to disentangle these factors to estimate these parameters explicitly. Okay. So the idea here is, instead of trying to estimate the parameters explicitly, only try to estimate what is required, what is important to be learned. So instead of making this z variable or z vector to be explicitly same as the parameter vector d in the first line, what if okay, this is Seems like the speaker is
Working now.
Mute my microphone. Actually, this one is being muted. This one is muted. Okay.
Yes, 1, 2, 3, 1, 2, 3, 1, 2, 3.
Maybe change the speaker. Use built-in. And let me use use my laptop speakers. Yeah. Okay. All right. I guess we'll only solve robotics once these problems are solved. So like every talk you give, there is some problem in the projector. Okay. So now instead of trying to estimate all the vectors in the parameter vector like friction, mass, etc., try to only understand or try to only infer the underlying basis of these parameters, which may be unique or maybe a very small dimension. So learn this Z. Okay. Now the idea here is very similar, and I'll go into more details in a few slides. Instead of trying to estimate these vectors through parameter, by minimizing the error in the real world, you can just try to learn a student policy or the Z vector by observing data in the real world. This was the idea in this paper, which was presented at RSS, again, one of G10's work. And in this, what they do is, instead of trying to estimate friction, mass, etc., you collect some data in the real world of the robot, and then you try to maximize the reward of the policy in the real world so as to estimate this value of this parameter vector Z, which is a lower dimensional representation of the whole system vector, which contains friction, mass, etc. So you take system parameters, privileged data, encode them into a small vector Z, and use that Z to learn the policy. Then in the real world, deploy the policy, collect some data, and try to find the Z which has highest performance in the real world. Okay. So if you go to carpet, the Z will highlight some variables which allow the robot to achieve maximum performance on carpet. Similarly, in other environments. Okay. And this paper got an award at RSS a couple of years ago. Now, instead of trying to estimate the Z vector, which can be slow at test time, you can also try to directly estimate the Z and amortize the cost into a network which takes history and directly outputs Z in simulation itself. So you can basically distill this teacher vector, which is learning from privileged data of simulator, and distill it to output the Z vector directly from the history of the robot. And we'll come back to this in a minute in more detail. And this leads to similar performance and slightly higher performance than a teacher slightly, sorry. This is the teacher vector, which has access to the exact system parameters, friction, mass, etc. And this is the student vector, which is trying to estimate the same values from history of the robot. So you are estimating different Z for different D. Yeah, I'll be sharing in one more slide. I'll go into more detail of this. In this paper, they don't regress to Z or D directly. They directly output the action, which is trying to mimic the action of the previous policy. So you don't worry about Z being same as D at all. All you worry about, I first learned this teacher policy. I learned how to output good actions for each environment. Then I take my history and then I try to regress the same actions from history of the robot. Okay, so this is a standard teacher-student knowledge distillation paper or idea, where you distill the policy of the teacher into a student. Correct. So it is still a single policy. And the hope is history will lead you to different outcomes depending on the situation. So it's left onto the hope than explicitly enforcing it. And we'll show in a minute how to explicitly enforce this idea in practice. Okay. But in any case, if you're very good at implementing this, you can get very strong results. So here is this result where this robot is put on this hiking terrace. This is from ETH, Marco Hotels Group. And this is a policy which is, this robot is blind. So somebody's controlling the directions of where to go. But here this is a demonstration of the low-level control in these robots. Now, this is the problem that I think you were asking about. Like, if I were to truly deploy robots in unseen scenarios, can I really expect that I have trained the system onto all possible variations to begin with, right? And once I go to new scenarios, if I want to adapt, how fast should I adapt? Should I adapt instantaneously? Should I take 1 year, half a year, whatever, right? So for instance, to give an example, let's say you learn to walk and you live in the part of the world where there is no snow. So you grew up in San Diego or something on west coast of US, or which almost never snows. And you then come to Pittsburgh, where I live, where it snows half the year. When you walk on ice for the first time, do you learn to walk all over again? Like, do you take again 9 months to walk on that ice, and how to, some people may take, but usually most people are very fast. We adapt instantaneously. We go onto a slippery surface, our motors actuate, and they give us signal as to how to adapt quickly to that scenario. So this kind of adaptation is very critical. This adaptation is part of almost every biological organism. And the main feature of this is very rapid. Like, you don't have time to fall on snow and roll multiple times to learn how to walk in like 100 trials or 200 trials. Even 5 minutes of data is too much. This has to be in a fraction of a second, because if you don't walk, you fall. And when you fall, you damage your hardware. So how do you adapt consistently in a very fast manner in an online fashion? So let's go to the idea again. So now, again, to recap, we are building a policy in simulation, which takes the state of the robot. And as we discussed multiple times, this policy is not invariant to all the parameters. This is rather conditioned on all the parameters to be adaptive of what the situation is. Okay. So just to make an analogy here, the analogy here is similar to robust control versus adaptive control in the controls literature. Like, robust control tries to find a policy that is robust in some domain, in some wide range. And adaptive control tries to find the system in which the robot is and try to adapt it. So all your fighter jets and all these things, they were earlier used to be controlled by robust control. And then there was some big failure and big loss, and people realized we cannot hope for a policy, even in a jet scenario, which is in the air, no contact, nothing. Even in that setting, robust control is not good enough to capture every possible setting. So you have to run on adaptive control. So now this, you can think of a deep learning version of adaptive control, where you are trying to take the system parameters, encode these parameters through a neural network into the small vector Z, and use this to condition the base policy to output actions. But again, the problem is, so let's call this extrinsic vector, because this information, this vector is capturing information which is extrinsic to the robot. Okay. But the problem is we cannot deploy this because this information is not there in the real world, and we want to estimate this very quickly in the real world in a fast manner. So this is not deployable. But the idea is, now we will try to estimate this vector online from history of the robot. Okay. Now this is no longer same as system ID, because in system ID, we are trying to estimate the exact parameters. But here we are trying to infer encoding of the parameters, which was directly learned to make the robot walk in scenarios. So this ZT is directly trained to capture only the essential information that is required to train the robot to walk. Okay. Now, one question you may say, why should history of the robot should have any idea about encoding of the friction? Like, how does history relate with fiction? Right? So note that there are two things in the history. It is a history of what was commanded to the robot and what it did. And the discrepancy between these two things contains information about the environment. So for instance, if I move my hand in air like this, if I apply torque of 1 unit, my hand moves 1 unit. if I repeat the same experiment inside water, for the same torque of 1 unit, my hand will move less. And the discrepancy is caused because of viscosity of the water. It's very dense fluid. I need more torque to move my hand through. So the discrepancy between what was commanded and what happens contains information about the history of the robot. So we can use this to train the system and estimate this online. But the best part is we can train both of these things completely in simulation without taking a single sample in the real world and then adapt in the real world. So just to recap, in phase 1, you train this system end to end and you encode the privileged data into Z vector and learn this policy. In phase 2, you copy the base policy as it is below, and then you directly learn to regress the Z vector, which was being estimated from this policy from the history of the robot. In simulation, you both have history as well as the data, so you can directly perform the supervised learning process. So first step is RL, second step is supervised learning. Okay.
So, part of this is done in simulation because you beat ground truth. That's what you have in simulation.
Yeah. But you could also do it in the real world, and the approach I showed before. But that would require many samples because, for instance, let's say there is no phase 1. You take phase 2. In the real world, you just have to take this policy and you try to optimize for Z vector such that the policy can walk. And this was a G and Sergey's paper at RSS, where they take 5 minutes of data on the real world and you use that data to estimate Z through optimization. So you can, but that is slow. But here we want this policy to be adaptive very, very fast in a fraction of a second. So we have to train this beforehand. Okay. Oh, sorry. There are 3 questions. I forgot.
So is the assumption that you mentioned before that measuring the X, you were mentioning about the door and you would have to measure how the door moves with the door.
Yeah.
Isn't that assumption also true if you want to infer those parameters from history of states and action?
Correct. So now we'll go more into this detail. But here, what you are relying on, so far robot is blind, so all you have is proprioception, right? So for instance, even if I have a drawer, my fingers can tell me, did I hold the drawer or not, or did I slip out of it? So you can use that information, and in simulation, if you fail, your joint angles will be very close to each other with nothing to block them in between. So you can use this information, and this is why this blind robot can still walk. But we'll show in few slides how to extend the same approach to high dimension input like vision and adapt from vision directly. But that assumption is not there because this X can be anything. It can be vision, it can see the world directly. There was one, yes.
So in essence, real cap.
Yes, so this is a very good question. So now in part 2, so there is some tutorial gap, but it's much lesser compared to part 1 because part 2 is trained from supervised learning and it is using Dagger. So this module, when you're training this, you collect data in the simulation wherever this module outputs the wrong Z. And then you train this module on the bad data. So in simulation, even when the robot is falling, you still learn to find the right Z from that falling example. So you are basically able to search the space very, very thoroughly, and it's just more like active learning. You go and poke every Z where you're wrong and you learn from that Z. So this has slightly better transfer in supervised learning. We know how to do supervised learning. RL, we are still struggling to figure out the optimization after so many years. But this is straightforward maximum likelihood, so it's very easy to train.
Do you ever experience any, let's say, collapse when training the environment of factor encoder? Because in the article, this encoder is trying to maximize that.
Correct. Yeah, so now this collapse could occur if you randomize a lot, but randomization has no effect on the performance. Like let's say, I would say you are moving your robot in the air and no contact is there. In those settings, you don't need to know the environment because it's very trivial. So then it will collapse. But wherever knowing the environment helps you, there's no reason for it to collapse, right? It's like I'm telling you in your ear, it's a carpet, it's a snow. So beforehand, and then you can of course use this information to walk as you like. Let's take one last question. Yeah, so we'll show how to combine these phases later. But one thing to note here is that when you're learning a simulation, you're solving two problems at once. You're solving the estimation problem as well as the control problem, right? And doing this end to end, you are both trying to infer it's a carpet and then learn how to walk it. So this procedure helps you get around that problem. Phase one is only control part, no estimation. Phase two estimation. So it's a nice decoupling of the system, and that helps optimization. And then you can deploy this in the real world. Just throw away that module on top, use this and that module. And now in real world, you can adapt this continuously, even though I cannot go back. Even though in training time, you adapted only once per episode, but at test time, you can continue to adapt as soon as you have new history of the robot coming into the system. So this robot adapts at a frequency of 10 Hertz. There is no sound here. And now you put this robot, it was trained only in that simulation, and you put this robot in the stair. It was never trained for stairs. It is being adaptive while in all these scenarios. In this setup. Is a patch on vegetation. It can adapt to this dip in the thing. One more example, adapting. So this adaptation is happening at a fraction of a second. So it's happening 10 times per second. So as soon as you have new history, you adapt the Z and you walk in all these situations. Now, one thing to note here is that you can adapt to all these scenarios without being ever trained on them. Like this gravel is very hard to even simulate, and it's unstable ground in there. So we also have some evaluation of how well can you adapt. So here is this environment where we add oil to the surface. This is very slippery, and we are draining down olive oil, and it may hurt some people. And so we also had plastic sheet on the legs and ask it to walk. So it can walk over this, but let's see it in slow motion to really appreciate how difficult the task is. You can see it is almost slipping, but can adapt in a fraction of a second. Now, like as Ken asked this question, like you can of course infer Z in the real world, but collecting 10 minutes of data in this environment is catastrophic for the robot. It will fall 100 times in that time. And here, this is happening at a fraction of a second. And this is very critical. So you can actually see it happening online. This is Z vector, and it changes behavior as soon as the robot goes onto the scenario and adapts its behavior. So this Z, like Z1 and Z5, they change their behavior immediately. So you can also adapt while the ground is moving. Yeah, and there are many more scenarios in the paper. But there are many still open questions. Like somebody asked, what about environment? What about vision? What about more complex robot? These are all quadrupeds. Like, can we go beyond quadrupeds? What about going beyond walking, by more agile tasks and more difficult tasks? Okay, so we'll discuss these questions very briefly in this time. So, for instance, more complex robot. So here, just locomotion is restrictive, and all of us want robots in our home that can help us do chores. So we add this arm on top of this robot. This is also paper in the same conference, and this is on whole body control. And instead of using very expensive robots out there, which we cannot afford in the lab, we build this cheap alternative. This robot costs around $6,000. It has an arm on top and legs. So this is trying to do whole body control from this setup. Okay. But the problem now, as soon as you scale these systems to higher dimensional, is that they have local minima. Local minima because arm wants one thing, legs want other thing. Like legs are more stable when arm is not moving. Arm is more stable when legs are not moving. So they go against each other. So what people do, they build these modular systems. You first optimize for arm, first then for legs, and then you try another system which puts them together. So very modular approach. Now, can we use simulations to rescue and learn this more end-to-end approach for doing this? Like, can you apply the same idea as before, like same RMA idea, like learn the Z vector and learn to regress it from the history of the robot? But the problem is, we made an assumption here. So nobody asked this question. We made an assumption that if I am trying to compress Z vector in the phase one, I'm assuming that the same compressed latent is also easily regressible from history of the robot. Compression does not imply predictability because there can be multiple solutions to compressing the system into a latent. But we can fix it simply. Like we should have fixed in the first paper, but we never got the need to fix it. But in this more complex paper, we find the need. So the way we fix it is by merging the phases together. You learn to compress the latent from the privileged data, while simultaneously making sure that the compressed vector is also close to the one coming from history of the robot. And then you use that latent to obtain the policy. Okay, so we call this regularized online adaptation, ROA. And we learn this to learn this whole body control. So here, it's a single policy controlling the whole robot, and all you specify is where the arm end effector should go. So you can see, as you take the arm below, the legs bend automatically. The robot body rolls, and all of this is happening through a single policy controlling this whole system. So we have this robot here at CoRL, and we'll do live demos as well today. You're welcome to try it on your own. Okay. Now beyond quadrupeds, you can also apply similar idea to bipeds. This is the same oily experiment, but now this is more expensive robot. We cannot just let it go automatically. So we have put some hinge on top, just in case it falls and we don't lose $500,000 in one experiment. Just trying to tow the weight with very heavy load in there. So other complex robots like hands, and there are works on hand examples, and it's a very studied topic. And there are work where people have used hand to, this is also a paper at CoRL, very recent, to manipulate many objects. This is a paper from NVIDIA, came out just a few weeks ago, where they use simulator to train this low-cost robot to simulate. And I can have Pulkit explain some work in his lab on hands. Okay, can use these slides. Show the hand one first, and then the ability. Yeah.
It's good now.
Should be good.
Yes. So, okay. So I guess what Deepak was, going towards was, using hands, which kind of connects back to what we were talking before, what was using tools, right? So now if we have to use tools, right, consider I have to use a knife to cut things, what we have to do is, we have to grasp the knife, then reorient it, right? And we need to reorient it so that the knife actually faces the fruit, which means that the sharp edge of the knife has to face a carrot to be able to cut, right? So in grasping, we have seen a lot of progress which has happened, and some of it also driven by, sim-to-real. For example, DexNet is a great example of, really pushing on that frontier. Then the other thing is, how to do reorientation, right? I mean, we as humans, do this all the time, right? We pick up the tool and reorient it. And, as Deepak was describing, this has remained a hard problem, but we have been seeing a lot of exciting progress in this domain, right? So, for example, there were demos from, Japanese labs, way back in 1990s, and more recently, by OpenAI, trying to do reorientation, right? And, So if we, try to look at all of these systems, the in-hand reorientation is a hard problem because your fingers need to make contact with the object. So you need to decide when to make contact, but then also how much forces to apply, right? So it's an instance of a continuous discrete optimization problem, which, is known to be NP hard, right? This is what, makes it really hard from a controls perspective. So one idea is, maybe we can collect lots of data and try to find an approximate solution to this really hard problem, right? Then to make it even harder, if we, look at, some of these, things that have been demonstrated, right? I mean, they only work with a few objects, right? They don't generalize to any new object. And, then some of these systems are working with an upward facing hand. Now, if the hand is facing upward, if your object is on the hand, the gravity supports it. So it's much easier to perform that particular task. But if you are cutting things with a knife, you're actually holding a knife in a downward facing fashion. Now, in these things, it is much more complex because you have to fight against gravity, right? If you make any wrong actions, the knife is going to really fall down, right? So in what Deepak was showing, there is this exciting progress in, again, leveraging simulations to solve these kind of problems. But here is some of the dirty laundry behind some of the sim to real work, right? So if you look at this demonstration from OpenAI, this is the suite that they use. There's so many cameras put so that they can precisely measure the simulation parameters or the real world state parameters so that they can bridge the sim to real gap, right? So while it was an exciting result, this makes it not very feasible to deploy it in the real world, right? So, what we have been attempting to do for some time is, can we, make the system work, but in a much more real world setup, by which I mean you only have one depth camera looking at it, and you have this, 4-finger hand, which is open source, and the whole setup on the right, costs less than $5,000, versus a shadow hand is maybe $100,000, and then all this apparatus is again $100,000 more, right? So could we get reorientation to work? And the reason to do reorientation is because to go to tool use, you have to reorient first, right? And this was some work done by Tao. And the paradigm remains the same, that we train in simulation and then transfer to the real world, right? So here is video of we can have many hands training in parallel. We can try to reorient objects in simulation, right? And then the way our policy is going to work is that there's a camera which is looking at the point cloud. So it's a depth camera which gets point cloud as inputs, right? And then it is going to output the joint commands, which is how much should each joint of my finger actually move, right? So it's very simple. You take in the positions of your joints, the depth, the point cloud from the depth camera, and you feed back how much the joints have to actually move, right? Now, if one has to have the system work, we need a policy which works from point clouds and then predicts actions. But now doing this in simulation becomes quite challenging. One reason is that the observation space is high dimensional, and training reinforcement learning with high dimensional observation spaces is challenging. But another more practical challenge happens is that if you have to get visual data, we need to do rendering. But rendering as a process is slow, which means that the simulation runs really slowly and you cannot perform this training, right? And that is what practically makes it very challenging. So, what we can do is, we can, because we had simulation, in simulation, we can play God. By playing God, I mean, I can access every kind of information about the object and the robot that I want. For example, things like object pose, how fast the object is moving, where the fingertips are all accessible. I don't need to put sensors to measure these things, right? And, because I know these quantities, this is also a low dimensional space. It is, maybe like 100 dimensions as opposed to an entire point cloud. And, we can train first a policy using this low dimensional state space. Then to work from the point cloud, we can, again, use this teacher-student paradigm where we say, now I'm going to learn this policy, pi st, which is going to imitate the teacher. So from point clouds, we are going to be doing supervised learning, right? Which is much simpler than doing reinforcement learning, right? So we had the problem, it's hard to learn with RL from point clouds are slow. So by following this teacher-student paradigm, we can bypass both of these problems. Everyone with me? Any questions? No. Okay. Right. So, here are, some, videos of this system. So on your top right, you're seeing the goal orientation. And, let's see, what the system is doing. Right. So this is reorienting novel objects that the system, did not, see before. Right. Here is, another example. And note, all of, this hand has no touch sensors. So it is doing this, purely, based on vision, right? And, you can, put, your household objects also, and, the system can keep on reorienting things, right? So maybe a couple of years back, a question was, hey, we can do sim to real, but, doing contact rich tasks was, quite hard because the contact models in simulation are not that good, right? So now with the work that we have shown, from many labs, both in locomotion and now also in this, task of doing in-hand reorientation, it seems like even for contact rich problems, sim to real can be a powerful paradigm to train policies. Right. So, and then, then what are the kind of things that one really needs to do to get sim to real to work, right? I mean, we discussed about some, theoretical or more algorithmic stuff, but, there is, much more than that which is required, right? For the theoretical or the algorithmic stuff was, how do we leverage the God powers of simulation by this teacher-student paradigm? But then there are other things, right? I mean, if I'm training even supervised learning with point clouds, it can take up to 20 days to train a policy. So, there's some work which needs to go in to reduce it from 20 days to 4 days. Then, if you are deploying on a real system, then we need to work in real time. So something needs to be done about that. We need to choose the right architectures so that we can do control, say, at 12 hertz, right? Then the other aspect, which is required is, somehow, identifying what are the parameters of the simulation in the real world, right? So we can, measure and estimate, what is the lag, what is the motor strength, and use those parameters in simulation, right? I mean, that also ends up, helping performance. And then there's a dirty laundry of, doing this reward shaping, that, I will get into. So it is, not just about, getting the algorithmic idea right, but there are many other things that need to be done. And there are many exciting directions in how can we remove or mitigate the manual tuning, which goes on in many of these things to have something which works out of the box, much like what is the scenario with supervised learning today, right? So, maybe that's all I'll say about, dexterous manipulation, but just wondering if anyone has questions or comments. Yes.
There have been experiments in humans where they show that if you take away some touch, even if you can look at the object, they have extreme trouble with doing dexterous manipulation. So, are there some experiments here where you assume that even with perfect visual perception, just need touch sensors and go around doing it?
So I think it's an interesting question of how much touch sensing we need. I mean, if you look at Intuitive Surgicals, which builds the surgery robots, right? People can teleoperate them without having touch sensors, right? So they can train the models to look at, visual feedback and estimate touch sensing, right? So I think maybe there's more investigation needed into how critical are touch sensing actually, right? I mean, I think if you have touch sensors, performance will definitely improve, right? Because right now you can only estimate contacts based on vision. Right. So I think there are. Okay. Okay. Any other questions? from anyone? Yes.
Okay, the results are really exciting. Curious about what you see as limitations maybe. Wow.
To 50%, right? So it is not a perfect system by any means. I think what this is showing is that hey, even for these unusual objects, we can get very far, but there's a lot more that needs to be done, which I'm really hoping is the last 5 to 10 minutes of the dirty laundry. And other things, I think is the hardware, right? I mean, the hardware is, like we just chose this because it was open source, but there's a lot that could be done to make the control be more compliant. Okay, so this was work from Vision, and now okay, so now this was working from Vision, so you have context in this place, and now what about doing legged robots also with Vision? Okay, now we already saw that in legged robots, blind robot was already very effective. It can walk all these terrains, and it's essentially blind. So why do you even need Vision? Like, is Vision only required for manipulation? Well, not quite, because if you saw the catch, the robot was going downstairs, not upstairs, because you need to see the stairs to go upstairs. Like walking on these stepping stones, which have gaps in between, you need Vision. So Vision is very integral. And the standard approach in controls community to use Vision has been to use Vision to build maps and then use maps to do control. Now, this is fine for high level navigation. Like I use Google Maps to find where my hotel is from here, but this is terrain maps. Like these are built at extremely high frequency, 25 Hertz to 500 Hertz. Now, if you just recall right now your office, do you remember how many stairs are on your way to from here to your office? You go there every day, you don't remember because you don't build map at that high frequency. And even if you were to build maps, they will be very, very noisy. And so like in these examples, I can see the map is extremely noisy. So to account for that, you add noise onto the control policy and make it robust. Okay, and you can see how noisy the terrains are across all these scenarios when you build map at very high frequency. Now in humans, it's exactly the opposite. We don't build terrain maps for very high frequency. We directly couple vision and control. This is one of my favorite papers from 1980s. This is David Lee experimenting with a kid, and notice how the kid falls as soon as he moves the walls of the room. Now the kid, she's not even touching the walls. He moves the wall and the vision system confuses the control of the body. So this and many other experiments in the last 30, 40 years have shown that vision and control in kids are very tightly coupled. There is no modular stages between them, and hampering vision hampers control and vice versa. Like if you want to try this experiment on you, like just go home and try this. Try standing on one leg with your eyes closed and your eyes open. You can imagine, you can feel a drastic difference between the two things. And standing does not even require any control. Like it's like or some control, but not very expensive. Like, and I close my eyes and I start to dabble. So this is very, very strong evidence of vision being tightly coupled with control. So we can also do the same using simulators because we have data to collect and they are high speed. So now in this result, this robot is walking directly from this input vision. There is no map being built into the scenario. And you can see it can do all these sorts of fine-grained locomotion, which are very difficult to do if you do build map of each of these settings. You can go upstairs, but not just any stairs which are almost as high as the robot itself. So if you notice very closely, it is not climbing the way humans climb stairs. It is climbing by taking its legs out like we climb walls or hurdles. So yeah, notice the stair is very high and can climb all this. Now, the reason for this is because you did not put any predefined leg controllers, and they were all learned through sim2real in simulation across diverse variety of terrains. Okay, so all these results were from a single egocentric stream of vision coming to the robot directly, no mapping, no terrain mapping. So it was operating directly from vision, and no predefined gates. So it learned to create its own gates, etc. Now this is a very low cost robot, so it's very small in height. One reason these robots are higher in height is to account for the world made for humans. We have a huge clearance from our hip joint to the ground, which these robots need to have, and this small robot does not have it. So it cannot climb upstairs like humans because it will hit the stair, cannot climb down, it will topple back. So it learns this gait of abduction, adduction. It pushes the leg out to account for these scenarios, and which leads to all these results in these diverse scenarios. Okay. Now, some example of map-free versus map-based. You can build maps, but then you have to also add noise to your controller. So this is a paper from Mark Hotter's group where they define what different kind of noise you can add to account for noise in the real world. So a step noise, global noise, local noise, and all those kinds of like 10 different kind of noises you need to add. And then of course, adding noise hurts the policy. So this is showing that you can either add noise and hurt the controller and then transfer, or you can learn a stronger controller without adding noise at training time. And here is again some dirty laundry in the spirit of CoRL. And here is the same robot. Now it's important, where do you put your camera? So on the left one, if you look at the camera is looking up, like completely forward. So it does not even see the dip. It comes back and just did not even realize that the terrain has ended. And this was basically a regular failure. This was the leg slipped. In this terrain, we tried 16 to 20 runs. This was the only failure we observed. But in the spirit of dirty laundry, we put it here. But the accuracy here was very high. And this was the only failure that we saw. Now, these were all walking examples, but about more agile tasks beyond locomotion. We can also, again, simulation is safe. So you can train in there and transfer to real world. So here, we try to get these dog-like skills of climbing on walls. So here is our robot dog trying to climb the wall using its legs by going towards the scenario. Now, this was again trained in simulation. This is very hard to experiment in the real world because the robot falls very badly if it fails. But it can climb with its legs. It can press button by balancing on 3 legs and then come down. So this is showing that with current simulators, the dynamicity of the task is like you can go to very dynamic skills as well. So you can see in slow motion how difficult this task is to both climb up and climb down. Now, what about other examples beyond walking, climbing? What about running? Can you build robots which can run faster than Usain Bolt or something? And this is an old result from Boston Dynamics. Trying to progressively go to faster and faster and faster robot. And here Pulkit will show some of work from his lab and on how can we achieve similar thing from sim2real and simulation-based approaches.
look at these videos, these quadrupeds are actually, walking quite conservatively, right? So in some ways, what we have is, quadrupeds which can be very robust, or quadrupeds, which are very fast, but in limited scenarios, right? So the question is, how could we, maybe get to robots, which are, agile and, still can go on any terrain, right? So now this, kind of goes back to the dirty laundry of training these systems, right? Suppose we are commanding robots for some, velocity, right? Suppose we want our robot to, sprint forward, but we also want it to spin, right? So we're going to give it, some, one second, let me hide this, right? So now, typically when we are training these systems, we are sampling commands from some range, right? So it turns out that if you sample commands from a small range, things work really well. And, you get to, these kind of behaviors. But, the moment we start to expand, things start to fail, right? And, let's try to understand, why this might happen, right? So, if you're trying to, spin fast and run fast, it is physically not possible, right? Because of centrifugal force, right? So you can either run very fast or you can spin very fast, but you can't do both of them together because of physical constraints, right? So now what you do is, there's a feasible region of commands which are there, and then there's an infeasible region of commands which are just not possible to do. So if, we uniformly sample commands, right, and we try to increase the difficulty of the task, what ends up happening is many commands become infeasible. And at some point, most of the commands become infeasible. What that means is that the robot just fails to learn because most things we're asking it to do are just not possible to do, right? So what we have to do is to kind of, come up with ways which can automatically learn, what is feasible and what is not feasible, right? So we can, design, curriculum strategies that automatically figure out the shape of what is feasible. And then if we train with this, things work, quite well, right? So if you do this, we can kind of, start breaking, the speed records, set on, this quadruped, the mini cheetah. But the fun thing is, we can also take it in the real world, right? So it's not just, working in labs, we can go this icy terrain, it's, balancing as it is spinning. We can also take it on, terrains which we did not model in simulation, right? So this is like a baseline controller struggling on gravel. And here is another controller, right, which was trained using some of the ideas we discussed, which is able to navigate, such terrains. Now, sometimes, when we are deploying things, things don't work well. In this run, a screw in the motor came out, right? So what you would notice is that the robot starts limping, right? But still robust, right? And the reason it is doing is because it is trying to do this online system identification. It realizes, hey, my leg is not as strong. So let me try to adjust for it and, still keep on working, right? So I think, what we have shown is, a bunch of exciting things which are happening in the domain of sim to real. And there are many exciting challenges and opportunities which are ahead of us, right? So for example, we have very fast simulation if our, state space is low dimension, right? Which is if I can access the state parameters exactly. But if you're doing things from vision, these things become quite slow, right? I mean, and one thing we know is that if we can do things with depth data, we can transfer from sim to real. But if you're doing things from RGB, it's a problem. So for example, in TextNet, we can train with a lot of depth data and then, get these, very robust, grasping policies to work in the real world, right? But then if we were to do things from RGB, that remains an open question because training with RGB doesn't yet transfer. Now, it's not just about vision, but we would want to do multimodal robot learning. So there's a lot of exciting work right now happening in building good touch simulators, right? So here is an example which is at CoRL this year, which is trying to build a tactile simulator. And so you can start doing, some, sim to real kind of stuff, right? For example, you can do peg in the hole in simulation and then transfer it on to the real system. Right? Now, you can also think about audio, right? Not just touch. So there are, good simulations like 3D World, which are out there, which are trying to, attack this problem. Then the other thing that we mentioned initially was, what about soft bodies, right? So I think there's, pretty, impressive and exciting work happening where people are trying to build, these soft body simulations. Another problem which comes up is how do we generate interesting content, right? If we have to have a robots, work in the house, there are all these, different ways in which I can arrange furniture and objects in my house. How do we get to that, right? So could we leverage, for example, recent progress in generative models to generate new content, right? Could we, use there's so much impetus, for commercial reasons in creating scans of our worlds and importing them into things like the meta world, right? Which can really drive, content creation in simulation, and how to efficiently leverage, crowdsourcing to create more content. So these are open questions, I think, which different, labs and groups are looking at, right? Then, other thing is, in some of the tasks that we were showing, learning simulation policies can still take weeks, which really slows down the iteration process. And what that has prompted is, research in differentiable simulation so that we can do gradient-based optimization and hopefully be much faster to train the policies in the first place. And then there are a bunch of methods that are trying to say, hey, if I can do gradient-based optimization, and if I can do gradient-free optimization like reinforcement learning, how can we combine those two things together to, learn faster? But this also ends up having implications for reinforcement learning algorithms that leverage parallelism, right? For example, a lot of the work uses PPO because PPO is an on-policy algorithm, which is easy to parallelize, right? But it is maybe not as efficient. On the other hand, Q-learning is much more efficient, but if you look at the literature, it's only been scaled up to say 200 to 300 environments. But now we can have thousands of environments. So can we, scale up Q-learning and, make use of this parallelism? Turns out actually, we can do this, right? So if we, compare with, PPO, SSC, DTPG, but if we build like a parallelized version of Q-learning, it ends up working much faster, achieves, better performance, right? Then, there is, the other thing, which is, hey, suppose I set up my simulation environment, I have a policy, I still need to define a reward function. Deepak showed this slide of, how many different terms one needs to set in terms of setting the domain parameters, but the same is true for reward functions. For example, in reorientation, my task is to reorient the object, but we need to have all of these other terms to say, okay, don't use too much energy, or, fingers should move in a particular way, sometimes to incentivize the sim to real transfer. And Ken, maybe this is also going back to one of the dirty laundry questions that you raised. Hey, what is behind the scenes? Now, there are, people who look at building better exploration algorithm, using things like intrinsic rewards or curiosity. But, how to balance, curiosity and intrinsic rewards with the task reward still, remains an open question, which, if we can make progress, it can, ease, reward design, right? Then lastly, when we are doing sim to real, the real world is always out of distribution. So we need something, to deal with it, right? So for example, right over here, the robot is trying to manipulate this, but this object, falls down, right? So what do we do when things fall down, right? So, one option is to do some real world, fine tuning, on the, like, so in the sense that the simulation policy is a pre-trained policy, which we can, do some adaptation or fine tuning in the real world, beyond, what we have been discussing. So these are just, open questions. I mean, I don't think people have, good answers yet, but I hope, we can reach to answers to some of these, questions, right? And what really makes the sim to real problem challenging is we say, hey, I want to go to the real world. But what is the real world, right? Is the real world, going on stairs? Is the real world, going under bars? Is the real world walking on sand, right? No one really knows, what the real world is. So what ends up happening is, as a designer, I have to think, hey, what are the training tasks I should train on? What terrains should I train my system on? How to set these simulation parameters, right? And the problem is there is no principled way because future tasks are unknown. So if I don't know what the future is going to look like, then how do I optimize for these, right? So we have made some progress, right, where the impact of these parameters has become lower by doing online system ID. But sometimes these systems fail, and if they fail, what you do is you say, hey, I think it failed for this particular reason. Then you go back, tweak your simulator, and then again deploy. But this loop takes hours and days, so it makes it really slow. Could we do something better? Could we somehow prepare for an unknown future, right? So just to make an extreme example, suppose if I'm training only on flat ground, could I now have a policy which can climb stairs, which can go under obstacles, which can walk on sand, right? So I think there's a lot of exciting work happening on out of distribution generalization. But another idea in that stream is to say, hey, what if I learn diverse ways of solving a task, right? So I learn to walk in many different ways, and then we can leverage that. Just to give an intuition, suppose what I did was not learn to walk in one way, but learn to walk in these many different ways. Now what we can do is, given a new task, we can tune the policy for that particular task. For example, suppose my robot is walking on a slippery terrain and it falls, right? The reason it felt is because its gait was very low frequency, right? So if you are walking on slippery terrain, you have to keep your feet close to the ground and move it frequently. So now what we can do is we can just increase the frequency of the gait, and the robot can successfully walk. So now this is now a matter of seconds instead of whole loop taking hours and days to recreate a training environment. Here's another example, but if your frequency is low, now you can't really climb stairs, right? Because you have to move your foot and the frequency will become slower, right? So now we can increase the foot swing height and decrease the frequency. So because the future is unknown, what we can do as machine learning researchers is to give tools which can allow someone to tune these systems very quickly in the real world, right? I mean, here's another example where you can tune the body length, the body height, so that the robot can go under the obstacle. Right? So here are some ideas of how we can deal with distribution shift, and I think it remains an exciting question. And maybe I'll end with the last part, which is I think training in simulation also offers very exciting opportunity of co-designing the hardware, which was not possible before, right? So for example, if you look at all of these quadrupeds today, all of them have a ball on their foot. Imagine if I said you have to run fast, but you have to do it without ankles. It's going to be so much more challenging. You might say, hey, why did people do this? Right? Because if you were in the model-based control pipeline, right, you would say, hey, I want to have a model which is easy to write. So if I put a sphere in my foot, it only makes a point contact with the ground. So it is easier to write that model and optimize through it, right? But, it limits what the hardware can do. But if you're going to prescribe to learning, we don't, we can, put more complicated things in the design and hope that we can just learn a policy instead of, writing down that policy, by hand or setting up that problem by hand. So for example, what you could start doing is you can start making ankles and try to optimize, both the hardware of how the ankle has to be and how the robot is going to walk. Right. And this is not just for locomotion, but you can start doing this, in manipulation also, where we can start designing, grippers, which are optimized for a particular task or a family of tasks, and then, go and manufacture them. So I think, the learning view of trying to do control opens other possibilities because I can also innovate much more on the hardware. So in some ways, it enables us to solve robotics in a full stack way, where control, perception, and the hardware can be optimized jointly. right? And then maybe I'll end by saying that we discussed about robotics, but there's a lot of exciting things happening beyond robotics where Sim2Real is used. For example, the Google Loon project, or the nuclear fusion project which DeepMind released, where they trained in simulation, but deployed a policy on a nuclear on a nuclear plant, not fusion. I think it was fusion, if I remember correctly. But it was fusion. Okay, it was fusion then. Okay, thank you. And then people are looking at urban planning applications and how to reduce traffic, so on and so forth. Right. So with that, I'm going to stop. And thanks so much for your time and for coming over here. And happy to take any questions. I think we went a bit over for a coffee break. So maybe we'll give so we'll take a 10-minute, 5-minute, come back at 11:05, 10:35. 10:35.
10-minute. Yeah.
So 10:40.
Yeah, sure.
Okay, so how about we still take a small break and we can resume at 10:40 for the next sessions. But in the meantime, if you have questions, I'm happy to answer them. And then up to you, Gabe.
Yeah. Yeah, and just to note the schedule, so up after the coffee break will be demos. So we're going to have 3 demos, followed by a set of talks by our invited speakers. Yeah.
Okay. Hello. Okay. Hi, everyone. My name is Naoki Yokoyama. I'm a 3rd-year PhD student at Georgia Tech. Unfortunately, we were not able to bring the robot with us to New Zealand, so we'll be doing a live stream of the demonstration, and the robot will be doing its thing from Atlanta. I have a helper with me at the lab who will be conducting the demo. Let me switch to his view. Let's see. I think I need to. Yeah, that makes sense. Spotlight for everyone. Is this good? Okay, so I am sharing the screen. Okay, let me just confirm with him that he's ready to start. Oh, all right. Yeah, I don't think we can hear Zoom because there's some audio issues here in the room. But I guess before I tell him to start the demo, let me just give some background. So here we have the Spot robot with the arm on the bottom right at the dock. It's going to be emulating a tidy up task where it will be putting away some of the toys that you see on the couch here. So we have 2 toy cars and a penguin, and it's going to be placing them inside of the boxes that you see kind of under the fire extinguisher thing towards the left. So yes, without further ado, let me ask him to start. All right, so it might take a little bit for it to stand up, but I can just narrate as the robot is doing its thing. So our method, we are learning how to do mobile manipulation entirely within simulation. And one of the highlights of the approach is that we restrict ourselves to only using data from sensors that are available on board of the robot. We don't use any privileged information about where obstacles are in the terrain or where objects, the exact object positions for the toys that we're cleaning up, for example. So here you can see the gripper is now extended. There is a camera in the gripper that we use to detect where the objects are. We leverage MaskR CNN for figuring out which pixels in the camera gripper represents the object we'd like to grasp. So here you can see our grasping policy is positioning the gripper so that it can grasp the penguin. So now that it's grasped the penguin, it's going to navigate to the place receptacle under the fire extinguisher. So the way this setup works is that we have 3 basic skill policies, one for navigation, one for grasping, and one for placing. And then we have 2 meta policies, and these 4th and 5th policies coordinate which skills will be used for the current time step, and the other policy will adapt the actions that the experts provide, just in case we want to override what the experts say we should do for the current time step. And for the navigation skill that you see being executed right now, it only uses a egocentric front depth camera you see at the front of the robot, as well as an ego motion sensor that just tells it how far it is and its relative heading from where it began, which is that dock area you saw it start at in the beginning. So here it's returning to where the objects are to find something else to put away. And yeah, one thing to note is that the obstacle avoidance is purely a product of the behavior of the navigation policy. We aren't making use of the Boston Dynamics API for planning around the couch and such. It's purely using the information that it sees in its depth camera to understand where it can go and where it can't go. So here it looks like it's going to grasp the yellow truck you see at the front right. Great. And then it's going to make its way back towards the place goal. And the way we train this navigation policy is, like I said earlier, entirely within simulation. We use about 1,000 real-world scans taken from like the 3D cameras that many real estate agencies will use to virtualize homes. And those 1,000 scenes include various civic spaces, such as residential homes, apartments, offices, hospitals, etc. And here, Nitish is showing that because this nav policy is very robust and doesn't need to leverage a map or anything, it can reroute and it can make a new route to the navigation goal without access to a map. So here, usually when the robot, even though it likes to go around kind of towards the right of the screen, clockwise, they went counterclockwise here. So basically, because we don't have a reliance on pre-computed maps, it can adapt to dynamic obstacles and changes in the environment. In contrast, the BD API, its navigation API can only use a pre-recorded map of the environment here. So one issue is that sometimes the drift of the ego motion sensor may make the robot believe that it's somewhere where it's not. But luckily, our meta policies are good at recovering from perturbations in even where the goal is set up. So yeah, in the spirit of the dirty laundry thing that Deepak was talking about earlier, one of the most common failure points of our approach is the MASCAR CNN. So because we aren't using like COCO objects, we had to make our own data set for object detection. And that data set was generated artificially using saliency detection methods and unlabeled video to kind of save time and not have someone manually annotate a bunch of contours and such. But as a result, a lot of times, especially when the robot is moving both its arm and its base, it can cause a lot of motion blur that also affects the performance. So since our grasping policy relies on the bounding box that MASCAR CNN generates, it does have a hard time grasping if the detector that we use doesn't have a good performance. but hopefully it will find its way. Another thing is that the patterns on this couch have also kind of caused a lot of the detections to be false positives. But let's give it a little more time. All right, you got it. So for the grasping policy, by the way, we also train that fully within simulation, and we assume access to a Mascar-CNN style object detector. Like I said before, it'll provide the policy with a bounding box of where the target object is within the depth image that comes from the depth camera located inside of the gripper. And that's what it uses to move each joint of the arm such so that the the gripper gets closer and closer to the object. So now that it's done tidying up, all that's left is to navigate back to the dock and then execute the BDI docking routine. It's not shown here, but there's a QR code at the back of the dock that the robot can use for making sure that it can sit down on the charger precisely. There will be a poster outside that will go into more detail about how the low-level controllers and such were trained. If anyone has questions, you can meet me outside in front of the poster and I'm happy to address them. Awesome. Seems like it's done. Oh, sometimes the charging contacts on the dock don't connect on the first try. Oh, and one other thing I may not have mentioned is that the gaming laptop on the back of the robot is what we use for execute all of the policies and doing the Mascar-CNN. Yeah, the robot sometimes flips over when it tries to dock, but that should be fine. All right, so that's it for my demo. I think I might have some time to answer a few questions if anyone has, but apart from that, that's all I have for the live stream. Thank you, Nitish, for helping. Yeah, it's also Nitish's birthday today, so happy birthday, Nitish. Okay, let me change the view back to the gallery. Yeah, is there, do I pin the speaker or something? I don't know. Okay, yeah.
Yeah, great. So thank you for the excellent demo. Does anyone have any questions? Okay, great. So I think we'll move on to our next demo, which actually has two components. So one is a real robot here on the stage, which I will set up over the next few minutes. Another is a demo on Zoom of a controller that we couldn't actually deploy in here because there's not really enough space. But my collaborator back in Boston will be showing robot soccer dribbling. So it might take like 1 or 2 minutes to get everything set up. Just bear with us in the meantime. Thanks. Right. So to begin the in-person part of the demo, so I'll describe a bit what I'm going to be showing. So this is the Unitree Go On robot. It is a robot that you can purchase today. They are actually being mass produced by Unitree. And it's a really great research platform in my experience. So it actually allows you to control sort of the low level motor commands yourself, which is good for sort of developing these low level control algorithms. I think what we just saw was a really great example of some state of the art work in the high level, where the robot is walking around and performing sort of tasks in the environment, interacting with objects. But I think there's also a lot of interesting work to be done at the low level when it comes to making robots that, for example, can balance better, can run faster, can traverse more interesting, challenging terrains. And so to this end, sort of first, I'll be demoing this controller that I've named Walk These Waves. It will be also presented at the conference, and it's an open source reinforcement learning controller trained in simulation, deployed in the real world, in real. And what's unique about this controller is that it's capable of an extremely diverse range of locomotion behaviors. That is, so it's only been trained in a very simple environment with flat ground, but it's learned a lot of different ways of getting from point A to point B. So the first thing I'll do is on the robot, I'm going to show you sort of the range of behaviors that it's capable of, and sort of allude to how these behaviors can be used to respond differently in different environments that are maybe outside of the training distribution. The second thing that you're going to see remotely is my collaborator, Yandam, showing how we adapted this controller to be used for software dribbling. So without further ado, okay, so the Walk These Waves controller. I'll turn that around a little bit. So yeah, so it's capable of sort of adjusting its contact pattern, and also this set of like 6 or 7 other parameters of its gait. And so those parameters are sort of continuous inputs to the ball that I can control using the knobs on my controller. So to show you what some of those are, and I might forget how everything is set up. Oh yeah, so okay, we can crouch, we can go high, so control over the body height, and of course, as well, the robot is moving. So all of these behaviors can sort of be combined together. You can also secure a different contact pattern, which is popping, but you know, I can switch between that. Prodding, pacing, sounding, sort of all of the symmetric quadrupedal gaits that we can get. Okay. Here we go. Okay, body pitch can also be controlled just using these 2 inputs. So again, this is all just one policy, but we can sort of modulate and combine these together, walking, turning with the body in different orientations. And the idea is that these are all sort of acceptable locomotion behaviors. They can all achieve high performance in the task, the simulated task of walking on flat ground. But each might adapt differently to a novel task. For example, trying to deliver a payload, the robot might actually want to tip its body to deposit the payload. Another example, maybe going back in continuous driving mode, would be the so parameters including sort of the foot swing height and the tape. So the robot can walk with a very high step frequency or very low step frequency. And at a lower step frequency, it's also much easier to lift the leg quite high, which can actually be useful. And I'll demo a bit later with more space in walking over some small ground obstacles that couldn't be traversed with a lower speed and which the robot has not been in the simulator. Any other? Yes. Okay. So finally, the last parameter I'm going to show you is this stance width. So here the robot has a really narrow stance, really wide stance. we can also do this. And of course, this can be combined with all of our other behaviors. And in this case, when the robot adopts the webcam, it becomes much more robust. It does. Whereas with the narrow scan, so, all right, that's our live robot demo for now. I'll be operating it more a bit later and happy to chat about it. But maybe let's connect with Yandong back in Cambridge, and he's going to show you sort of how we adapted this controller to also play soccer. So, yeah, how can we?
Hello, everyone. Can you hear me?
This one? Yeah. It's possible to make that. Okay. Yeah. I think. Yeah, no, can you hear us? Can you
Yeah, I
talk?
can hear you.
Okay, great. Yeah, do
Great,
you want to say?
great. Finally,
Yeah.
finally. Yeah, so hello, everyone. My name is Yandong. And as we can see that we are here at the real soccer field. And I'm going to show our soccer project, which is able to control a quadrupedal robot to dribble a soccer ball in the wild. And the output of this joystick on my hand is the commanded ball velocity in X and Y direction. And then we can then let's see how this project is going on and how our policy is able to control the soccer ball. How about we first control it to go to the goal that is behind it right now. Oops. I think that's a little bit because the light is kind of shooting directly on the ball. And then we can, let's try again on this. How about we do a 180-degree turn right here? And then another 90 degrees. And then another 180 degrees. Okay. So we can see that although sometimes it will miss the ball because of the color-based ball detection method right now, but most of the time it is able to dribble the soccer ball following a commanded velocity on my joystick that is in my hand right now. Then let's do another experiment to see whether our robot can dribble a soccer ball to the goal that is on the other hand of this soccer field. I think the distance is around like 200 meters. Let's see whether it can dribble it safely there. Wait. Oh, I think I commanded to the wrong direction.
Oh, yeah, Doug, maybe we can conclude the demo there. And I can just talk a little bit more in person about sort of what the challenges of robot soccer are. But yeah, thanks so much for calling in. Awesome demo. And so, I mean, as you can see, in Boston, I think it's 5 p.m. right now, so it's pitch black outside, which makes perception a little bit challenging. But we were still sort of able to demonstrate these really interesting sort of dribbling behaviors. And so why is soccer dribbling like a hard or interesting problem? Well, you can find out more at our poster outside at the poster session later this afternoon. But to summarize a few key points, I think first, sort of the dribbling demonstration shows that even when we train a controller using these sort of structured gates, it can be a strong base from which to adapt in order to perform some task that actually requires like substantially different motion. In this case, sort of kicking turns as sharp as 180 degrees. So a second point that's key is I think the soccer dribbling task involves two sets of affordances. It involves the affordances of the robot walking on terrains, which, for example, I think the interaction between the robot and ice versus the interaction between robot and grass would be very different. But the distinction between walking on grass versus walking on pavement might not be very large. In contrast, the ball, it's much lighter, and it's making this like much broader contact with the surface. So actually, if you think about what would happen to a soccer ball, if you kick it on grass, the drag will slow it down really quickly. And if you kick it on pavement, it'll just keep rolling forever. So there is sort of a second set of dynamics to consider, the dynamics of the ball against the ground that can sort of elicit some rich and interesting behaviors. And yeah, to find out more, you can come to our poster outside later. But with that said, maybe I think we'll move into the a few lightning talks next by some contributors of posters. And but first, I'm happy to take any questions if anyone. Yeah. Yes. Yes. Yeah, so there's no MPC controller, so it is just a neural network. The inputs are just the sensor data, and the outputs are joint position targets for PD control. But what we did is we provided some structure through the reward function of sort of not a complete reference trajectory, but some rewards, for example, on like making contact with the ground at the desired time that are dependent on an input to the policy. So the result ends up being some gates that look very like structured and MPC-like, even though the whole thing is just a neural net. And I think the benefit that we can potentially get out of that is that, and which we can also get from like both from going to the simulator to the real world and from going to just like real world flat ground to diverse environments in the real world, is that even if one strategy, for example, like dragging your feet or adopting some particular contact pattern works in a simulator, it might not generalize to the real world. So by building in these biases, it's difficult to quantify in simulation alone, but through some sort of proxies for generalization, we're trying to show that this can help. Yeah. Yeah. Yes. So I guess the reward function, it is computed from, I guess, the instantaneous state of the robot. Of course, it might be using some things that can't be measured in the real world, like the body height is not being explicitly estimated, but it is through the reward function, like the robot is being incentivized to adopt like sort of continuously parameterized target body height that gets input to the policy. Yes, but there's, I guess, yeah, it's all being computed as a reward. Yeah.
We generate diverse motion to, for example, capture the velocity command. So to check the velocity command, there can be lots of solutions. So to get that lot of solutions, we can tune the word, change the word design to adapt to this happen, but can we just like generate diverse motion like
yeah, so it's a really good question. And I mean, there are definitely, I think, works that have explored this, maybe not in like the full like robust sim to real setting, but in lots of other RL problems. How can we generate diverse gate like behaviors in a latent space, whether it's like quality diversity or some sort of maybe unsupervised skill discovery type of methods that use like a diversity metric. And yeah, so I would say like one item of maybe it could be considered dirty laundry is that it does take a lot of sort of human knowledge to design a reward function that specifies working structured, like functional structured gates. On the other hand, I think it is also, it can be difficult to define a diversity metric that actually produces viable gates in the real world. Like a lot of the time, if you train with like totally unsupervised diversity, you might get some, for example, like lots of like three-legged walking gates, things like that, which are certainly diverse. But I think at least thinking about it from like first principles, I would say you definitely want some constraints on your diversity, or at least I found it easier to start from there. And with the goal being that a human pilot can sort of intuitively modulate these parameters instead of just searching in this big sort of unstructured space. Yeah. Okay, great. If there are no further questions, then I think we'll move on. So I think maybe we'll transition for about 3 minutes and then bring the next, I think probably the lightning talk on a poster. So yeah.
Can I ask who do the talk first?
Yeah, I mean, you can go ahead and start, I think. So yeah.
Okay. Okay, can I start? Can you see my screen?
Yep.
Okay, so yeah, so let me start. Hi, I'm Minjo So, and I'm glad to present my work, Learning to Walk by Steering, Perceptive Quadruped Locomotion in Dynamic Environments. Okay, so let me talk about the motivation first. Deploying the robot in real human environments remains an open challenge. So human environments are usually cluttered with human moving dynamically. So robot must simultaneously perceive a surrounding from onboard extroceptive sensing, anticipate nearby human motions, and perform agile locomotion to avoid obstacles and humans. Also, such environments are usually designed for humans, so it is also important to understand symbolic meanings and follow human manners, such as West sign like this. So the goal of this work is to develop a perceptive leg locomotion framework that operates in real-world environments among human and clutter. However, if we use a method of training in simulation only, we encounter the problem of sim-to-real gap in visual observation and the difficulty of simulating human behaviors. So here I introduce our framework Prelude. Inspired by recent advances in data-driven method, our approach uses deep learning method models. So rather than an end-to-end algorithm, we design our method to harness complementary strengths of imitation learning and reinforcement learning. So this allows the learned model to be deployed to real hardware with minimal domain gaps. Our key idea is to decompose the locomotion problem into high-level navigation and low-level gate generation policy to realize target commands. From this decomposition, we train the high-level navigation controller with imitation learning. And by learning from human demonstration, the model acquires the ability of complex spatial reasoning of motion prediction. Furthermore, imitation learning on real-world demonstration data eliminates the reality gap. Then we train the low-level gate controller with reinforcement learning in simulation. This will allows discovering versatile gate styles. So let me talk about then some method briefly. So for collecting real-world data, human demonstration data, we want to ease data collection, we design a steerable card platform rather than using a real robot. We record human actions and observation, including raw RGBD images and simultaneously. So in this way, we eliminate the need of manual labeling of human actions. Based on this data set, the high-level navigation policy is trained to generate the target velocity command. For training, we only used 240 demos within 3 hours of work clock time. The low-level gate controller is trained by reinforcement learning in simulation by using a distributed PPO algorithm. When you deploy the policy in the real robot, the navigation policy generates desired velocity commands from visual observation. Then the low-level gate controller actuates the robot joints to track the velocity commands. So finally, we deploy Prelude in real-world environments. As you can see, we successfully deployed Prelude in unseen cluttered environments with different light conditions and various crowd behavior without any further fine-tuning of models. So here's the conclusion. In this work, we introduced our hybrid learning framework, Prelude. It harnesses the complementary strengths of imitation learning on real-world human demonstration and reinforcement learning in simulation. To this end, we designed an intuitive card platform for collecting human demonstration data easily. So for training, we only needed a handful of offline real-world data to train a high-level navigation policy. Also, finally, we deployed a Prelude to the real-world environment. So we showed that the trained policies can be transferred to the real robot in a zero-shot manner. The resulting gate controller is robust enough to track complex navigation commands from the high-level navigation policy. Also, Prelude can be generalized to unseen dynamic environments. So this is all for my talk. And if you feel interested in my research, please drop by my poster. Thank you.
Great, thank you, Mingyo. Does anyone have any questions? I have a question. So Mingyo, what do you think are the like most challenging environments for this task of sort of obstacle avoidance and navigation?
So usually the most challenging environment is that even though robot can avoid recognize the humans, but if the space is not enough to avoid the humans, then actually the robot got in trouble. So I didn't include the video in this slide, but so we actually set up a very challenging environment with the narrow corridor. So that in that case, robot need to stop and wait for humans to pass through.
Great, thank you. Any other questions? Okay, with that, I think we'll move into our invited speakers. First, I'd like to welcome up Jia Tan. So Jia is a staff research scientist at Google Brain Robotics, where he leads the robot locomotion and safety teams. His research has expanded our ideas of how learning can be integrated with systems for robotic control. And today, Jia will be telling us about his team's approach to learning locomotion in the real world.
Thanks for the introduction.
So, if possible, if you can share your screen to Zoom as well.
Okay, let me try. I need to unmute myself.
You can speak through here, so you need to mute here.
That's great. Morning, everyone. My name is Jay. I'm a research scientist at Google. And early this morning, Pocket spent 15 minutes to tell us how hard it is to learn in the real world, to motivate learning simulation. That's great. I agree with you. And so we need to tackle the hard parts heads on and learn in the real world. Since 2018, we published the first paper that applied deep reinforcement learning on leggy robots. Until this year, early this year, that ETH demonstrated an impressive array of locomotion skills in the wild. It has been only 4 years. And in these 4 years, we have seen tremendous progress in leg locomotion fueled by these powerful deep reinforcement learning algorithms. Most of these papers focus on the sim to real approach. So today I want to share a different perspective. Is it possible that we can directly train locomotion skills on the robot in the real world? You probably already know this. Pocket gave a very good introduction why simulation is important. They are fast, they are safe, they are scalable. We need to face and solve this sim to real gap problem. Over the years, you have the researchers have developed a wide variety of very effective technique to overcome sim to real. And you probably already learned the most important ones this morning. So no sim to real gap is no longer the biggest advantage of learning in the real world. So why bother? First of all, learning in the real world frees you from additional modeling efforts. Things like deformable body, granular materials, fluids, and all these things are very difficult to model. Even if we can model them in simulation, usually it takes orders of magnitude longer time to simulate than real time. In these cases, why not just learn in the real world? But most importantly, as we all know, scene creation or asset creation is always a bottleneck in simulations. In my opinion, it is nearly impossible to capture the diversity of the real world in simulation. But ultimately, our robots need to operate in these complex, diverse, and ever-changing human world. So it seems that learning in the real world is unavoidable. But learning in the real world is really challenging. First one is data efficiency. As we all know, reinforcement learning is notorious data hungry. Learning in the real world means that you have to collect data in the real world for weeks or months. And the data collection process is really tedious. Human supervision is needed. The robot learns to walk away from you, step on something, flips over. Now you have to run towards the robot, pick it up, bring it back, reset experiments. It's a very tedious process. Last but not least, safety is a big concern. Robot can do real damage in the real world. Sometimes the robot think, oh, I have a great idea, I want to try it out, then break its limbs. Over the years, our team has breakthrough many robots that lead to very costly repairs. So today, the lesson I want to share with you guys are really expensive lessons. Over the years, the team has built a complete system that enables the robot to learn in the real world. So this block diagram looks very complex. So let's simplify. We start with safe and efficient reinforcement learning algorithms. On top of that, we add a shielding mechanism to guarantee the safety of the learning process. The key idea of shielding is that you have this judge of safety, we call safety critic. Then it will judge whether the proposed action by the agent is safe or not. If it's not safe, it's going to query some other policy so that it can override the original unsafe action to guarantee the safety. I'm going to talk more about shielding later in today's talk. And the team has been building and revising this whole framework for about 4 years now, and we have published a series of papers on different components of the system. And today I'm going to give you a high-level overview of the system. Let's start with the safe and efficient reinforcement learning algorithm. Just a quick recap of the problem we are trying to solve. We want this robot to learn in the real world how to move. And we choose a reinforcement learning setup. That means we need to define the observations, which are all the onboard sensor can collect. Then we define the actions as the desired motor angle for each degree of freedom. Then there's a PD controller to transfer it to torques. And we crafted a reward function that encourages the robot to run as fast as possible towards a certain directions, to turn as fast as possible, and to minimize the jerky actuations. By strategically specifying these weights, W1, W2, W3, you can encourage the robot to learn different tasks, such as moving towards different directions or turning. And these are all pretty standard stuff when you try to apply reinforcement learning to leggy robots. We choose to use an off-policy learning algorithm called soft actor critic, or SAC, to solve this problem. SAC is a off-policy learning algorithm, as I mentioned, so it can reuse the data that was collected before, so it's data efficient. But more importantly, SAC has these two terms in the objective function. The first one is reward maximization, so all the reinforcement learning had that. The second term is to maximize the entropy of the policy. So it encourages more exploration and sometimes leads to better data efficiency. But the problem of having these two terms in the reward function is now you need to introduce a hyperparameter to balance them. And it turns out to be the quality of the learning is really sensitive to the choice of hyperparameters. You have to tune it per robot, per task, per environment. Doing this is possible in simulation, right? You can spawn multiple simulations with different hyperparameters and then just pick the best one. But in the real world, trying one time is already maybe weeks. Doing multiple training on hyperparameter tweaking is nearly impossible. So we need to figure out a way that we can train these things more efficiently. To do that, we reformulate the entire SAC into a constraint formulation. So now you move the second term into a constraint. The entropy need to be bigger than some threshold, but you only need to focus on one reward function. Although you still have this one hyperparameter, the threshold for entropy that you need to tune, But empirically, we show that this formulation significantly reduces the sensitivity of hyperparameter tuning. And basically, you don't need to tune the hyperparameter in the real world. Another benefits of a constraint formulation is now you can add more constraints. For example, you can add a constraint for safety. So in this project, we constrain the roll and pitch of the base so that the robot will remain more stable during the training process. So does it work? Now, this figure shows you the comparison between with and without safety constraint in terms of the number of falling during the entire training process. We can focus on the orange curve and the blue curve here. The orange curve shows you that if without safety constraint, the robot falls over 100 times during the training process, but the blue curve is with the safety constraint, it only falls about 40 times. In addition, we find that this constraint for safety does not impede the performance of training. Again, take a look at the blue and orange curve, you'll see that actually having a safety constraint slightly bump up the learning speed as well as the final performance. This is what the training process looks like. You put the robot down on the ground, it tried to randomly exercise its limbs. After 35 minutes, it can make some progress, but still falls from time to time. And after 32 minutes, the robot can effectively move forward and backwards. And about 2 hours later, the robot can move towards different directions and also turn very effectively. We also try to the real world training on different type of terrains. Here is a memory foam and also a rubber mat with a lot of crevices. The reason is because of these materials really difficult to model in simulations. This highlights importance to learn in the real world. So one limitation of this work is that although we significantly cut down the number of fallings throughout the entire training process, it still happens. Anytime it happens, it results in very costly repair. So to eliminate the unsafe events as much as possible, we introduce this shielding mechanism. And the first step is to train a safety judger to tell whether an action at current state is safe or not. In safe reinforcement learning, people usually categorize the state and actions into two buckets, right? The safe set, unsafe set. Most of the time, it's very easy to tell whether things are safe or not. If the robot is standing very stably on the ground, yes, it's very safe. If the robot has fallen on the ground with belly up and the legs flaring in the midair, it's unsafe. But the tricky part is really near the boundary. If the robot is about to fall, but we are not sure whether the policy is powerful enough to save the robots. So we have to wait for a few seconds to see whether it's actually falls or not to know the safety. So that's a tricky part, and we want to quantify that. To do so, we borrow ideas from reinforcement learning. Reinforcement learning has this Q function, which measures the expected accumulated return over time. How about we can define a Q function for safety? We call it safety critic. It measures the expected probability of the robot falling over time. Let's take a closer look at the definition. If the current state ST is outside of safety set, the second indicator function of the safety critic becomes 0. And now Q safe for this state, no matter which action you choose, equals to 1. The safety critic equals 1 means the robot is not safe. In contrast, if the current state is way within the safe set, the first indicator function becomes 0. Now we need to roll out the entire trajectory using the policy, the safety policy. Suppose at a certain point, the trajectory ends up outside of the safety set. At this terminal state, Q safe equals 1, as I indicated in the previous slide. And this 1 is going to back propagate towards ST due to the recursive definition of Bellman update. So at this ST, you are going to get a Q safe between 0 to 1, depending on how many steps you are away from failure, and also the discount factor. But remember that reinforcement learning is stochastic. If you roll out the same policy one more time, you might get a slightly different trajectory that is entirely within the safe set. So we use the expectation over all the trajectories of your safety policy to calculate the safety critic. Overall, it captures the expected probability of the robot falling in the future. Once we train this safety critic, we can then threshold in different ways to decide whether state action pair is safe, unsafe, or unsafe but still recoverable. Once the safety critic decides that now the state action pair is not safe but still recoverable, we are going to query a pre-trained safety policy so that we can save the robot. In this project, we have a very challenging locomotion task we want to learn, that is to balance on 2 feet. And you can see that if we just use safe reinforcement learning algorithm without the safety critic and safety policy, the robot falls from time to time, very often. But if you have the safety policy, so the robot will start from collecting data right now. If it detects it's about to fall, it's going to lower the center mass, spread the legs out, take a few steps to recover balance. Once the robot thinks, oh, I'm ready again, it's going to collect data again for the task. You might be curious, how do we design this safety policy, right? There are 2 very important criteria. The first one is it should be able to save the robot from a wide variety of falling configurations. The second one is it should be easy to do sim to real because we train this safety policy in simulation. To satisfy both needs, we start from a hierarchical setup. In the lower level, we use MPC. Okay, so it reasons about the contact force of the stance leg and also the next foothold location of the swing leg. It's a very powerful algorithm for balance, and people have investigated decades on this algorithm. On top of that, we train a safety policy using reinforcement learning, which monitors all the states about balance and output the variables that can modulate the low-level MPC. And empirically, this thing works really well. We can zero-shot transfer the safety policy to the real world, and it can save the robot most of the time. And here you can see that this is the trend. I think this is one of the late policies for learning to balance. It can balance for a few seconds by jumping continuously multiple times. And over the course of the entire training, there is about 5 times of falling in total, but compared to hundreds of times if you don't have a safety policy. At the same time, if you look at the learning curve, the blue curve shows you the robot learned the task well, better and better. And the red curve shows you that the number of triggering of safety policies goes down. It means the robot not only learns the task, but also learns to be more safe. In rare cases, the safety policy failed to rescue the robot, and the robot still falls to the ground. This is usually the biggest bottleneck of the entire system because a human intervention is needed. Someone needs to reset the experiment. And it really limits the scalability of the system because you have the human to babysit the robot. To overcome that, we have trained a automatic reset policy where the robot can always flip over from different falling configurations and stand up to continue the data collection process. I'm not going to dive into detail of the training. Feel free to chat with me afterwards to learn more about this project. Overall, the learned policy is really agile and works almost 100% of time in different type of the environment. With this reset policy, the robot is doing some task, no matter it trips over by itself or pushed down by some adversarial PhD student or some curious kid, the robot doesn't really care. It will just flip back, stand up, continue what was doing by the robot. So with the entire system, I just want to summarize. We found that the learning in the real world for quadrupeds is really challenging, but it is essential for these robots to operate in the complex, diverse, and ever-changing human world. So our team has developed this autonomous, safe, and efficient learning pipeline that enables the robot to learn in a lifelong fashion in the real world. In the last minute or so, I want to zoom out and focus on the big picture. Over the years, we have learned how to build and leverage faster simulators. For example, also at CoRL last year, the ETH and NVIDIA teams has showed us that locomotion skills can be learned in Isaac Gym within 10 minutes, and then zero-shot transfer to real robots. Also, we have developed a lot of effective zero-shot or few shots learning algorithm to overcome the sim to real. For example, the RMA mentioned in the morning can effectively adapt the simulation policy to novel real-world environment within a few seconds. The question really is, if these methods stops working because the real-world environment is so out of distribution from the training data you get from the simulation, what should the robot do? The robot really should be patient, collect data on the spot and learn from these data, and then figure it out by itself. It might take more than a few seconds. It might take actually minutes or even hours, but it's important that robot need to figure it out by itself. This requires a safe and autonomous real-world training or real-world fine-tuning pipeline. That's exactly what the talk is about. We have made a lot of progress, but we barely scratched the surface of this entire problem. I still believe that it's an underexplored problem, but it holds the final missing piece of the entire sim to real puzzle. I want to thank all my collaborators and also thank you for your attention. It's hard for me to hear. Sorry about that.
What happens when the robot has to interact with us?
When the robot has to interact with us.
Yeah. So the research is not a robot.
So I think that's a benefit of learning in the real world. Well, it doesn't really matter whether the robot needs to interact with object, because you have the object present there in the real world. For example, dribbling on the ball, you can always learn with the ball present in the real world. So it's actually a benefit compared to learning simulation, because in simulation, if you need to interact with an object, you have to create an object.
But you have to reset the object, which is much easier.
That's a good point. It really depends on what kind of the problem you're looking at. If you are pushing the door open, and if there's a spring to close the door automatically, yes, you can do it. But if it was stable, yes, the reset is a problem. I Google actually a lot of the training data in the real world, and we do engineer the real world a little bit so that we can automatically reset.
Perhaps whether the safety grid is also task dependent, or you have to choose the record for each task.
Yeah, so the safety grid is the task dependent, but we don't have the additional input for the task. We only have the state and determine whether it's safe or not. It means that for different tasks, currently you have to learn different safety grids.
Do you think there will be a way to create a general safety rating that applies to several tasks?
So the question is it possible to have a general safety policy that's worked on all of us? I hope so. I think we have hope. The reason is as we start to see the other fields of robotics, when they do multitask learning, once they introduce larger and larger models with maybe additional input for tasks, or even without that, they will start doing really well. So I believe that the safety critic is just another Q function. So it's very likely as we train on multiple tasks and into bigger models, and the safety critic can solve it. There's no more questions. Thank you very much.
All right, thank you, Jay. So our next speaker is Nicholas Hees. So Nicholas is a research scientist at DeepMind, and his work in both algorithms and applications has advanced our ability to apply learning algorithms in challenging control problems. So today, Nicholas will tell us about his recent work in this space. Yeah, so if you're okay.
Testing? Okay. All right. Thank you. So to pick up on this theme that has been so effectively discussed this morning, and I really appreciate Deepak and Pulkit's overviews of these challenges. What I'd like to do is well, first thank my my students who are there's 5 of them here in Auckland, and I was happy that this came up actually in Jay's talk about talking about Isaac Sim, and well, I think it's important to recognize that there's been an enormous amount of progress in the past year in from Isaac Sim. And also, as we just heard from Nicholas, this has been happening from DeepMind and Majoko. The progress is really impressive, that the simulators are getting much better. And I was also very happy to see this. Yuval Tassa visited us last week, and he was talking about this new modeling of suction, which is very important for industrial applications. And I believe it's the first step in modeling suction in simulations. And it's actually quite a subtle problem, because suction, just getting the seal right on the object and the reaction of the object to forces as an object is lifted with a suction cup is also very subtle. Now, I also want to come back to this point about system ID that Deepak made earlier, that there is very well established subfield of system ID out there. And the important thing, it sounds like what is needed here, which is we want to be able to identify the system, the robot, and then and instantiate the simulator to match it. The challenge is actually that it works if you have a very nice, well-defined model of your system. But unfortunately, that almost never is the case with robots. So we can't fall back on these very well-established subfield of system ID. And just let me give you one example. This is the classic double pendulum, right? And if you're going to do, for example, system ID on something just as simple as this, 2 joints in the presence of gravity, good luck, because it's pretty well defined what the masses are, et cetera. But there's a very, very small, and actually this slide shows it better, a very, very small parameter there, which is your starting conditions, that will give you extremely different behaviors. And just if you watch this for another few seconds, you start to see how these will start deviating. And this is a point I want to just emphasize, that we want to be careful about claims about simulation, no matter what. There's going to be ambiguities and indeterminacies, and they're non-trivial, right? It's not minute. It actually can, the difference between these 3 systems is enormous as they evolve. So we have to have our eyes open. And I think whenever we talk about simulation, we have to acknowledge and grapple with the challenge that simulation is never going to match reality. This is one I also like to share. Some of you have seen this, but this is a robot just pushing an object across the table, and we just repeating the same initial conditions, the same control motion, and as you can see, the result is extremely different. Now, this is not just a matter of getting more data. I mean, I always love the distinction between aleatory and epistemic uncertainty. Epistemic uncertainty says if we get more data, we'll be able to predict this better and better. But there's this other quantity, the aleatory uncertainty, that remains, which is we're never going to be able to actually predict this object ever. It's undecidable because it depends on this inherent surface micro topography that is impossible to know because it changes and it's lying underneath the object. So there's no way to sense it. And if there's a minute change, a little asperity, a little grain of sand, the result is going to be very different. Okay, so we just cannot predict and cannot simulate that, and we just have no way of knowing. Now I want to go back to DexNet, and this is Jeff Mahler's PhD work, and our attempt there was to try to get a handle on this in the context of grasping, which was to start by acknowledging all of these uncertainties and say that you can capture this in some degree loosely with a graphical model where there's the conditional probabilities and relationships between these random variables. And I say random carefully here because it's easy to just say, well, the friction is, mu is a random variable, but mu isn't even the right model for a lot of contact friction. So we can approximate this, and then the idea was to look at perturbations in that graphical model, and then evaluate the stability of a grasp, the equilibrium of a grasp for a variety of different perturbations, and then integrate to come up with an estimate of the probability of success. So just to make that a little more clear, this is an example of an object, say the red pipe fitting, and we want to decide what are the probability of success for these different grasps. And the idea is, what I'm proposing here is that what we did was to look at particular nominal grasp like this, check if it is successful using, again, very standard Cartesian physics, Newtonian physics, and then do perturbations. So we consider all the essentially uncertainties that we have, we perturb it, and then check for which of those are successful, and then integrate those to figure out what is the probability, given that we don't know what state we're going to actually get. What's the probability that that state is one of the successful ones? So after we do that integration, we can come up with a measure like this that you see on the left. It's has a much lower probability of success, much less robust grasp than the one on the right. And I hope that matches your intuition as well, right? It's just the one on the right was self-aligning, self-stabilizing. We can also do something similar in the realm of in perception, because again, we have a lot of noise and uncertainty there. I would also make a similar claim that we'll never know the precise position orientation of all points in a scene. There's some kind of uncertainty principle there. It's just, no matter how good of our sensors get, there's always going to be uncertainty that's inherent there. So what we want to do now is we'd like to be able to infer the state of the object just from the sensor data, but that is not always possible. So what we do here is this is exactly the same form of a sim to real. And here we take images, simulated LiDAR images, and match them together with a particular grasp and a pre-computed or pre-estimated robustness. And each one of those becomes a triplet, an example that we then use for supervised learning to learn this function, that if you're given the Y value, given the grasp, that the network will take all these examples that were generated again in sim and then learn to predict R, the robustness. And then if you have, in that network, actually you can get the error very, very low. So it's actually remarkably good at predicting the robustness. And then you could use that inside a loop, a control loop that considers different grasps, runs it through the network, and finds one, chooses one with a high quality or robustness. So, and that idea, just for its objects in isolation, you can generate lots of examples, but Jeff also suggested that he would do this with bins of parts. So objects, lots of objects in heaps. And we haven't seen too much of that today, but that's actually another big challenge in grasping, because grasping something that's sitting stably on a table is extremely difficult. But it's even harder if those objects, if it's sitting on top of a bunch of other objects, because you don't have, there's many more 3D poses it can be in. And when you go to make a grasp attempt, the forces can actually act very unpredictably because it's not necessarily in a stable pose. So, but Jeff was able to do something very analogous, again, creating artificial heaps and generating and learning a function that worked in that context. And here's the result. This system had fairly high accuracy, above 90, for unseen objects in real, and actually even higher precision. So there are failure modes, and I really think it's really important to emphasize those as much as possible. And so we haven't solved this problem, and I think that's a danger to say that, I mean, sometimes, you know, we've talked about this a little bit today, right? The OpenAI. Remember that when OpenAI, after they announced this, you know, the fine print was that it worked about 20% of the time. And after a huge amount of volume of data that was collected and applied to it. And basically OpenAI decided that they didn't want to do robotics anymore after this. They got out of the business. It made some good, they actually ended up in another good business of ChatGPT, so I can't argue with them. But it was interesting because we, you know, to claim this is a big success is, you know, very questionable. And the issue again was the gap, this sim to real gap that we were facing. And I also really like Deepak said, here's this page in the appendix, right, of that paper that showed, you know, here's all these parameters that we varied, and here's how we varied them. Now that is really important to me because I think that this is another issue we should think about, which is if we're going to do domain randomization, the key is the random part of that. And so this is a common system that does domain randomization that I found online. It's just a little video showing this. And, you know, what does it do? Well, it just randomly puts textures and modifications onto the object. And I look at this and it, you know, I don't know, my intuition is this can't be the right way to do things because the space of possible textures is just so vast and there's so many different ways you can randomize that scene that it seems hopeless that we actually want that that's going to be an essential part of learning. Now, what I want to say is that structured domain randomization or domain perturbation, it means let's not randomly choose these values, but let's use them very strategically and find values that will actually reflect what we experience in reality. And so there will be things we can't know. So I say I want to reassert that, but also that it's usually within ranges of uncertainty. So the mass, right? We know that there's a range of mass, or the position of the center of mass. We know that, but it's not sort of a huge wide distribution. It's usually fairly narrow and maybe Gaussian, or there might be some structure that we could use. So this is why I've been very interested in what we've been calling real to sim, and this has been mentioned here today as well. The real to sim part of this is let's tune our simulators as best we can before we start learning in sim. Because the challenge again, and this comes up again and again, is that sim is very intoxicating. It's you know, it's sort of a, what is it, a habit. It's habit forming, right? You look at something and it looks really compelling, and you start to believe in it, right? But we need to use it with caution. You know, it's a little bit addictive, so we have to be careful about it. And what I would say is, let's put effort into trying to make these simulators not only look interesting or look compelling, but also actually be physically compelling and physically close. So when we talk about the soccer, for example, right, you could do a fair amount of time because you have a beautiful soccer demonstration. It looks good, but then take it out with your real soccer robot and see how, within the same inputs, how much they match up, and then tune the simulator to accordingly. So here's an example that we looked at, which is again a toy problem, or you know, sort of an arbitrary artificial problem, but we called it planar robot casting. So we're particularly trying to demonstrate where this happens in the case of frictional dynamics. So we're just, as you can see what's going on, we're just trying to get this endpoint to a target. And it's kind of related, there's some real world analogies to this. And, but the gap is that we can't, that if we try to train this with a sim, it's easy to build a simulator for this system, but the question is getting a good simulator. So the idea here is that we wanted to start with the real rollouts of this system, as you see on the far left here, that are, actually the video is not playing, but it's basically we have a camera overhead, we send these commands, and then we try to tune the simulator so that the results of the simulator are closer and closer to what we're observing in reality. And again, knowing that we'll never get it perfect. So, and it's not even repeatable, right? So this is actually, that comes back to the aleatory uncertainty, that if you give it the same initial conditions and you run the robot again, the endpoint is not always going to end up at the same point. That's the aleatory uncertainty, the same as pushing the object across the table. So you have to acknowledge that. But given that, there's a range of where the object will actually end up. So this is the real to sim part of it. And how do we tune that? So I think this is also very understudied. This comes back to the point about system ID. And one technique that's out there, differential evolution, I don't want to claim that that's the answer by any means, but it's a method that's used to fine-tune systems. And in our case, we were able to get some good results. This is comparing the results, and if you actually pay attention, it's the median line in the middle. That what is the error between the position of the endpoint and the target as a function of the length of the cable. So 61%, you're not doing well. You get it down to 27% with the Gaussian process model. If we just use the real data and we train a policy, we get it down to 11%. So or 15%. It's quite a bit better. If we use the simulated data, we get it to 14%. Again, much better. But if you put them together with the sim to real pipeline, we get it down to 8%. So we've really gotten something out of this combination of systematically training. And this is an illustration which can generate where there's ellipses here that indicate the aleatory uncertainty that's just inherent at different points in the state space, and how you are able to reduce that with the policy. So here's an example of it working. And again, the trick here is we throw a quarter on the table, the camera sees it, then it tries to match it. So here, and so in the spirit of dirty laundry, there's an example, totally missing. All right. So, and there's a lot of those, and I think it's important, and I want to encourage everybody here: show your dirty laundry. There's nothing to be ashamed of. It's actually really good, and it helps us. It's where the interesting things happen. So that's what my statement today. I think this kind of workshop is extremely timely and extremely relevant. This is what I think there's enormous potential here, and the progress that we've seen today even is super exciting. And to have the major companies like NVIDIA and Mujoko, Google behind it, really, there's a huge momentum. And the key for us, I think, is having our eyes open, knowing how to really continue to push at that gap that's still going to be there, and in some senses always going to be there, but to cope with it and find ways to live with it, minimize it, and then make the best of it. Thank you. Yes, Deepak.
In the last example, do you have some understanding of the failure modes? This accuracy thing that existed, or because the success was extremely impressive, but failure.
No, exactly. No, we don't, and that's a great point. We really don't have a sense of when it's going to fail. What we can do is we can give you the range, right? A nice ellipsoid that will say, here's where we expect it to fall, and that's pretty consistent within that. But again, it depends on where the initial and target are in your workspace, because there's going to be parts that are going to have much more uncertainty than others. But when it comes up in two different outcomes, no idea. And this is what we were saying about pushing an object across the table. Again, you just don't know. And I want to say more strongly, you actually can't know. But that's not something we're going to fix as scientists. So we have to accept, just like the Heisenberg uncertainty principle, there are things that we're not going to know. So how do we acknowledge that and then work within them? No, okay, so one of the key things to know here is that I also think this is, I'm glad you asked that question, because I want to get us away from this idea if it succeeds, it fails, right? Those are two sort of unnecessary, binarization of the outcome. There's an error, and that error varies across the scope of the workspace. So let's try and really look at that and study it, right? And so it absolutely, that error, but one thing that's interesting is once you've done this a number of times, the error doesn't suddenly jump out, some huge amount. You can bound it within that region. So this is what I want to say, is that also one of the other dangers I see is that we're happy to show our videos of our robots doing incredible things, but we have to show them not working. Okay, please do that, because it's really important to show those failures. And then for us, not just to show them as a necessary, an annoying, we have to get this dirty laundry out of the way. No, the dirty laundry is actually where there's an interesting question. And so let's focus on that. And, never, I would say, never reject a paper or anything like that for pointing out its own limitations. That's what we're here to do. Yes. Yeah. No, thank you. Okay, that's a great point. No, I haven't thought that through and to have a real process to do it, but I think there is a way. So I could just say for DexNet, what we did was we spent time, for example, with the camera, actually look at the parameters of how much noise we got in those Z values, the depth values, how much error we got in the motion of the arm. So we actually just measured it. And again, it was all about ellipsoids all over the place, trying to basically say, what's the errors? And then say, okay, let's sample within those. And a lot of times, for example, the point clouds that you get out of the depth camera typically they are pretty nicely Gaussian. But there's additional outliers, right? So that happens too. So, but this is the realm of good statistics. How do we fit good distributions to these models and learn their parameters? And I think that just having, and I think Deepak mentioned this at the beginning, was an actually systematic method to go about and learn those different values, right? What are those ranges? How do we do that? Maybe there's a form of system ID to learn what is the error range for each of these things, and then plug that into your simulated system. So that would be a nice research. I mean, there's a lot of opportunity there. Good. All right, way in the back.
For some of the examples that you showed about explicit system identification or certain parameters,
yeah,
it makes sense in certain cases, truly where we want robots to go is unstructured, you're extracting the substance that you don't even know how to parameterize. In those settings, do you have any intuitions about what parameterization to go after? How would you go about this or
Okay, excellent point. I will say mea culpa, because I agree with you. I think you're absolutely right. There's a lot of things that even the list of parameters, I couldn't even start to begin to list, right? I like the rapid motor adaptation, RMA, approach of saying, there's some vector of extrinsics. I don't even know what it is, but I'm just gonna basically treat it as this latent vector of variables that I'm gonna somehow fit back to the scenarios of what I've observed, right? That's one way to deal with it. I think you're right. For example, the torsion, when that rope example I showed, the torsion of the rope was a parameter that doesn't exist in most simulators, by the way. They don't have it. Isaac Sim actually has a parameter for that. We have no idea what that is. So we kind of try to estimate it. But you're absolutely right. There's going to be other parameters that are extremely difficult. This is in a nice lab environment, right? It's a very controlled two-dimensional problem. But yeah, you try to take this out into casting a line in a real setting or something like that. It's going to be much harder. So that's a great point. And I think that's maybe an even stronger statement, which is we can't even know the parameters, let alone model them, right? So how do we deal with that in our simulator, right? So I think that's another great challenge, is trying to figure out how many parameters there should be, what they should look like, and how we should learn them, right? Just learn those and adapt. By the way, I very much accept this idea of not being robust to all parameter changes, but rather adapting to them is a much better idea.
Taking that argument one step further, does it even start to question the idea of a simulator?
Maybe. maybe. Yeah, I think it's actually a great point. So maybe the idea of any simulation, right? There's going to be, we say that, there's this gap. And if I'm going to want to put my robot out in a very, a vastly varied, diverse set of environments and conditions, then I'm never going to capture all of them, right? And so I think that in some way, then, the answer is, yeah, I don't know. I mean, I think we could probably start with some simulation, but use it cautiously. That's my biggest message, is that simulation is a very powerful tool, but it has its, it can also really be dangerous in some sense. And so we have to keep our eyes open. That's really, I think, one thing I want to emphasize. Great. All right, listen, lunch is happening. Let's go. All right, thanks everyone. Thanks, guys.
Yeah, thank you, Ken, for the great talk. So we will have, it's lunch right now, and then we'll have our poster session starting at 1:30 and sort of running through. There'll be some conference events during that time, but actually coming back to this room at 3:15 for the remainder of our talks.
So hello everyone, I'm Niranjan and I'm going to present our work on cascaded compositional residual learning for interactive navigation. This work was done in collaboration with Sihoon Ha and Irfan Isa from Georgia Tech. Navigating real-world environments often requires rich interaction with nearby objects, such as doors or other obstacles. But learning such behaviors is a challenging problem. With traditional RL, the extent of reward engineering and hyperparameter tuning required makes these training of these skills impractical. Further, even if we maximize the reward objective, we might still have a large sim-to-real gap. The core idea of our work is to avoid training new skills from scratch, but instead train them as constrained residual perturbations to a combination of pre-learned skills. Consider a straight walking policy that outputs the target joint angles given the state of the robot. If we perturb this policy just right, we can get the robot to turn. Notice that these perturbations are conditioned on the state of the robot. We can think about these perturbations as learning a residual policy that augments the output of the base policy. These perturbations can just be added to the base policy, but as the number of skills increases, this becomes suboptimal. Multiplicative compositional policies, or MCPs, offer an alternative solution by combining policies as a multiplicative composition of weighted individual outputs. These weights control the relative importance between different skills and can be learned during training. However, we don't just want any perturbation that can get the robot to turn, as we still want the turning behavior to look similar to a walking skill. To ensure that we do not deviate too much from the walking skill, we constrain the perturbations that we add. We impose two penalties on the learning framework: a residual weight penalty that maximizes the contribution of the residual to the final composite, and a residual magnitude penalty that keeps the magnitude of these perturbations to a minimum. We modify the traditional PPO objective by adding scaled versions of these terms. We take the skills that we learned as residuals and we add it to our skill library. These skills can be used to learn even more skills by learning additional residuals. For example, we can use the turning policies we learned earlier and combine them with the walking policy to train a robot to walk to a target location. This creates a dependency graph of skills where each node is a skill that is learned as perturbations to a combination of parent skills. We can scale this to an arbitrary number of levels. In our work, we trained a total of 10 skills, of which 8 are built as residual skills on top of other skills. While we manually design the skill graph by using some intuition about skill dependencies, we can also automate this process by searching the space of all possible skill connections. Since each skill is built for a different task, they might not share the same observation space. For example, reach target skill requires the location of the target object that is in close proximity to the robot. While using the skill, the goal location has to be generated intrinsically by the agent. To compute these intermediate goals for the parent skills, we define a synthetic goal network. But this module again can be learned while the policy is trained. So here's an overview of our approach. To summarize, we build new skills by recursively learning perturbations to a library of pre-learned skills. Since each skill might have its own observation space, we have an observation selector that selects observations relevant to each skill. In the image, we show the architecture of our interactive reach policy. Note that the skills like reach target can themselves be composites of subset of skills that belong to the library. Using this framework, we train RL policies in simulation and transfer them to the real world without any fine-tuning. So let's look at the kinds of behaviors that we can generate using our method. So we train all our policies in Isaac Gym by simulating 4,096 robots in parallel. So first, we start with a straight walking skill that's trained from scratch using RL and ensure that the skill transfers reliably to the real world. By perturbing the walking skill, we then learn a turning policy. So we test each intermediate skill to ensure that we have successful sim to real transfer. So next, we train the robot to open a door with an automatic closer. The robot is penalized if its body touches the door and is rewarded for walking forward and pushing the door open. In the real world, we track the state of the robot and the door by using mocap markers. So here's a video of the same policy in the real world. So while navigating indoor environments, the robot might need to traverse narrow spaces like crawl under furniture. Here we present a crawling skill that's trained as a residual to the walking policy. Next, we build more complex skills using the combinations of these learned skills. To reach a target, the robot uses a combination of turning and walking skills. And here we transfer it to the real robot by adding mocap markers to a sheet of cardboard and then making the robot navigate to it. Since the robot only cares about the relative location of the target, it can adapt to external perturbations. We also train a manipulation policy that can push an object to its target location. And we transfer this policy to the real world as well. Finally, we train policies on challenging interactive navigation tasks. The robot must get to a target object placed somewhere in a two-room house. As we show in the video, we transfer this to the real world as well. As we show in the video, the robot crawls under a desk, navigates to the door, pushes it open, and then proceeds to reach the target. Please check out our paper and supplementary material for more details about our method and videos of other skills. So in this figure, we visualize the trajectories taken by the robot to reach all the grid corners in the environment from a given starting point. We compare our approach 3 baselines. Notice that while simpler tasks like opening a door can be tackled with curriculum learning, for more complex tasks, our framework offers a better alternative. Our approach reaches a success rate of about 72% on the challenging interactive reach task, beating the baselines by a large margin. Further, while success rate can be high in simulation for a particular policy, it does not guarantee successful sim to real transfer. Our approach yields trajectories with better quality that use lower average torque compared to baselines. And this is because the policy learned by the baselines are only constrained on the reward function, and the exact nature of the behavior is difficult to control. Similarly, while training skills without a residual, the robot can still sometimes get to the target object, but then the quality of the trajectories is poor. So to summarize, we proposed cascaded compositional policy learning, a technique to build a set of interactive behaviors by recursively leveraging a set of pre-learned skills and task-specific learned residuals. We use this framework to achieve a high success rate in a challenging interactive navigation task. And for future work, we're excited about multiple directions. One extension of our approach is learning vision-based control policies. So instead of training a vision-based policy end-to-end, we can add image condition perturbations to a pre-trained walking policy and make it avoid obstacles. So we have some promising results in this direction. Another problem that we're looking at is improving sim-to-real transfer by learning residuals directly on real-world data. Thank you.
All right, thank you for the great presentation, Niranjan. Are there any questions?
Thank you.
Yeah, so I have one question. I guess towards the end, you alluded to potentially learning these residuals in the real world. So do you think that that can work better than like trying to learn policies from scratch in the real world, or like what real world tasks do you think could potentially be improved by learning residuals?
Yeah, that's a good question. So I guess like one of the challenges with learning in the real world is like just the amount of data that you need to collect while training your RL policies. So one of the things that we observed by sort of using this residual framework is that you can start with some policy that's like not as good as you want it to be, and you can just improve on it by adding residuals to it. So let's say you have a walking policy trained in simulation, and you have the sim to real gap that you want to overcome, then you can just learn residual perturbations to this policy and improve its performance on the real world.
Okay, thank you, Niranjan. I think up next we'll have Matthew presenting his work on soft robot subtool transfer.
Hope everyone can hear me. So my name is Matt Walter. I'm a professor at the Toyota Technological Institute Chicago, or TTIC. And this is joint work with my now former student, Chip Schaff, who unfortunately, or fortunately for him, graduated and went to Tesla, and Audrey Siddall, who is a research faculty at TTIC, who is now at McGill. So they should, they really did the bulk of the work. And just one shameless plug from TTIC. So TTIC is a very small, basically a computer science department university in one. Okay, it's not updating. Let me see. I'm seeing the slide. I don't know if you see the mouse anywhere.
Can you drag it to the left and see if it appears here?
I thought I saw it. It's here. There it is. So up, is it up? Nope. Down? Left? No? Right.
It's coming. Okay, you have it back here. And if you share screen again.
So my shared desktop one, not Keynote. Ah, yes, okay. Okay, perfect. Okay, so anyway, long story short, TTIC is hiring. The deadline is technically passed, but if you're on the job market for a faculty job, TTIC is a great place to be. We have this research assistant professor, which is a 3-year endowed position, no teaching. You get a research budget, but you do not have to teach. You can if you want to. And of course, we're hiring in tenure track. And tenure track, we teach 1 quarter a year. So it's a pretty nice gig. Okay, so the problem that we're looking at, and this is something we've been working on for a little while in my group, is this problem of looking at optimization problems in robotics that involve reasoning over the physical design of a robot and what we refer to as this computational reasoning. So one example of this might be, and what I'll focus on in this talk, is designing legged robots. So say you have a simple legged robot like this, and you have the luxury of designing the robot. So how long each link should be, what its diameter should be, maybe you can add new limbs, change the joints, etc. That's the physical design, and there's some parameters that define that design. Then in this case, there's some computational reasoning. This is the control policy that takes observations of the robot, observations of the state, and outputs actions. You know, most often this is going to be nowadays a neural network, and that's a computational reasoning piece. And these two problems are coupled. Some designs make control more robust, control more easier, more effective, and vice versa. So really the two problems should be considered jointly. And that's what we're looking at, is these problems where we want to optimize both this computational reasoning piece and design piece in the context of a given task. So this is, again, you can see a different robot that's tasked with locomoting over walls and showing different robots from this distribution. And I'll tell you a little bit more about that in a bit. Okay. So again, we've been looking at this in many other domains. Another might be learning to design a new manipulator and the grasp policy for that robot to perform some task, you know, some simple pick and place task in this example. Another is designing a sensor array. So if you're familiar with the Bayer pattern, imagine you can design a different allocation of filters on an image. So that's your design space. And then you have some inference space that's going to do, say, semantic segmentation. Can you optimize both of these jointly? It turns out that there are some alternatives to the Bayer pattern that work better for particular neural network architectures for semantic segmentation. We've also done this in the context of beacon placement, where we can choose to place beacons in an environment, so sensors. That's the design space. And then the computational reasoning piece is this neural network that does inference, takes readings from these sensors and spits out whatever the phenomenon we're interested in. Okay, so we're going to look at this in the context of legged locomotion. And we've known for a long time that you can get very effective control policies when you have when you're able to exploit the dynamics. So a famous robot here is this Tad McGear's walker from 1990, where he shows that you can actually achieve a stable limit cycle in the upper left there and get this robot to walk ballistically. So with no external energy, only gravity, walking downhill. And we've seen many other success stories here, most recently Atlas, where again, you're exploiting the properties of the design to get very effective controllers. Okay, but what we want to do is we want to optimize these both jointly with little to no domain knowledge. So we want to do this in a model-free way, just entirely a data-driven approach. And we're going to formulate this as a reinforcement learning problem, where critically, we want to search over the space of designs with the constraint that we have one control policy. I guess if we're in New Zealand, one control policy to rule them all, in reference to Lord of the Rings. We have one control policy that's taking in whatever the observations are, some parameters of the design, some parameterization of the design space length of each limb, and has to control all these robots. And that has a number of benefits, because this control policy, as I'll show, is able to learn about the space of designs, to learn which designs are better, which are worse. And I'm getting, okay, let's see, sorry about that. I don't know what I did. Okay, so anyway, so we wanted, there's one control policy to learn to control all the different designs. Okay, and again, for the sake of time, I'll skip ahead, but I'll just show this pictorially how we represent this problem. We represent this again as an RL problem, where you can imagine, again, we have this design space. I'm showing this in 2D, the length of a limb, the width, etc. Each sample from this design is a separate Markov decision process, so a separate MDP. And so what we're going to do is we're going to start off modeling the distribution over designs, assuming we know nothing other than maybe a limb cannot be less than 1 centimeter long and can't be longer than a meter long, say, for example. But otherwise, it's effectively uniform over this space. And again, each one introduces a separate MDP. And our goal is to learn both the parameters of the design distribution as well as, let's see if I can, as well as the parameters of the policy that maximize expected reward. Okay, so I'm going to show this so that we're going to have a uniform distribution over the space of designs. Again, I'm showing this maybe as a mixture of Gaussians in practice. We're going to sample from this distribution that gives us a set of MDPs. We're going to train a single control policy using soft actor critic. So on the right underneath that, which I'm not going to mess with this, shows this neural network picture of a control policy. We're going to train that control policy over all the samples from this distribution. Then we're going to sample some more, give it to this control policy. And what this control policy is doing is it's learning about the space of designs. And then what we're going to do is after some time, we're going to go and we're going to update. So again, this is updating the control policy, sample some more. And then eventually what we're going to do is we're going to use policy gradient methods to update the design distribution, to focus distribution on higher performing designs, where higher performing is measured using this controller that's trained or learned in conjunction with this distribution. Okay. And we continue this process. And we find that this works very well. It's not terribly sample efficient, and so all of this work is done in simulation, but in simulation it's very effective and outperforms a number of baselines, including hand-designed robots. But the question is, well, again, this is done in simulation. Does it actually work in the real world? So we looked at this in a different locomotion task, which is a soft robot locomotion task. Audrey is a soft robotics expert. I am not, though I've learned a bit more than I did when I started working with Audrey. And we look at what's called new nets. So we have these leg-like appendages here that have the openings in them. You inflate them with air and they bend. And if you can coordinate if you can control the pressure. If you do it in the right way, you can get this robot to locomote. So I'll show this robot here. It's named after a shepherd out of Harvard. So it's a very classic pneumatically actuated walking robot. So this is Audrey's implementation of the shepherd walker with a hand-tuned controller. And you get this, the forelegs share one pressure regulator, the hind legs share another. And if you coordinate them just in the right way, you can get forward motion. You can get this robot to crawl. So in our case, we wanted to see if we can discover maybe a better design and control pair. So we have our design space here. We have a rigid disc, and now we have 3 pressure regulators, and we can choose at one of either 8 or 16 locations whether to place a leg there. And if there is a leg, which of the 3 pressure regulators should it be connected to? So if there are more than 3 legs, they're going to at least a pair is going to have to share a regulator. And I'm showing some different designs here, and the colors indicate which pressure regulator. Okay. So the challenge with this is that simulating soft bodies is notoriously difficult. It's ridiculously slow. So the classic method that people use, one of them, is called SOFA. That's what we use. So there's this famous saying by Rod Brooks, simulation is doomed to succeed. Well, in this case, simulation is doomed to be slow. This is 100 times slower than real time, far too slow for our method. So we have this choice. We want to speed up the simulator so we can actually make it usable by our algorithm. We want to do so in a way that preserves the accuracy of the simulator. And there's been a lot of work recently developing differential simulators where effectively you're trading off accuracy for speed. But that's not something that we wanted, right? We wanted to be able to get the speed, have our cake and eat it too. Get the speed as well as the accuracy. And that's really what the focus of this paper has been on, is really this sim to real transfer. And the way that we do this, and again, it's related to what Ken mentioned earlier, this real to sim to real, there's in system identification, it's one technique that people use is model order reduction. So you want to find some projection of the space. In this case, it's the vertices on some mesh. So I'm showing a mesh from one of the limbs. And you want to find some projection here such that you have a lower dimensional representation of the mesh, but one that preserves accuracy. And so we would do trials where we actually would try to find the projection. Again, this is the real to sim to real that gives us behavior that matches what we're seeing in the real world. And really, it's not sexy, but the secret of this effort has been really to make the simulator as realistic as possible while preserving computational efficiency. And that's now the challenge with this. Again, if you do this wrong, you get simulation is doomed to succeed. You get the sliding maneuver, and this is great for our algorithm because it just wants to move forward. It says, wait a minute, if I inflate all the legs, I'm just going to magically slide forward. It's very happy, and it's going to quickly settle on a design that does that. And of course, obviously, that's not going to transfer to the real world. And so we need to be very careful about how we do this model order reduction. But another key issue is that this model order reduction is well known when you have a single design. When we have our design, we can come up with the reduction that preserves accuracy, we get computational efficiency, we're done. But in our case, we're searching over the space of designs. So we can't reduce every possible design. So we have to be smart about how we do this reduction. And one of the focuses of this paper, and I should have said this paper was at RSS this past summer, is to do this in a modular way, where we can effectively, by very carefully doing this, we can come up with an algorithm that allows us to reduce just 2 parts, the disk that the legs attach to, and a single new net. And we're doing this in a modular way such that we can assemble an arbitrary design and reduce design. So we reduce once, and then now we have a model order reduction that works for any possible design in this design space. Okay? And the algorithm proceeds much like the other one before. we have a discrete set of designs, about 7,000 when you include symmetry. We're going to maintain a distribution over each one of these designs. And again, it's uniform in the beginning. We're going to sample a bunch, and for about 200,000 episodes, we leave that distribution uniform and keep training our controller with different samples. I think it's 96 samples to learn something about this design space. And then, this shows that here. So in this case, these are different designs in the y-axis. This is training time. So what we're showing actually is a histogram over the design. So most of the designs here are not doing anything. It's inflating the legs, but the robot's not going anywhere. There are a small number that are. And so that once we hit 200,000, we allow ourselves to update the design distribution. Put more mass around higher performing designs and less around lower performing designs. And what I'm showing you is chasing out the mode of this distribution. Okay, so this is all in simulation. The good thing with soft robots is they're pretty easy to make. So we can fabricate them and we can try these robots. So we took our top performing designs. Again, we have a distribution. So we took the designs with the top 5 masses and we manufactured them. And we ran them in the real world. And as a baseline, what Audrey did is she took her shepherd walker, tuned the control parameters. It's a very simple sinusoidal pattern for the fore and hind legs with the phase shift. That's a classic approach to making these locomote. Tuned the parameters in the real world, and then we have them effectively compete. And we find that our top performing design performs about as well in the real world. This is forward progress 20 seconds. So these are not running. Certainly these are very, very slow moving robots. Moves almost as far in the real world as it does in simulation. That becomes less so for other designs. We attribute this, and it's in the paper, to modeling friction. The baseline actually doesn't move in simulation, but does move in the real world, and that's where we were tuning it. Okay. So again, for the sake of time, I'll skip forward. But one interesting thing we found with our robot, and we think that this allows it is better at transfer, is it has 2 hind legs. So the left is going to the right that are on different regulators versus the baseline that has both hind legs on one and forelegs on another, and 1 foreleg, not 2. And so what it learns now is it can deflate the hind legs in such a way that it tilts, and the tip of the leg, only the tip of the leg is making contact. So there's very little friction, so it's able to slide. The classic sinusoidal pattern is really exploiting friction, and if that friction, if there's a mismatch in that friction from sim to real, for example, it will not transfer. Parameters that work well in the real world will not work well in the simulator, and vice versa. We speculate that because our algorithm is less dependent on friction, or learns designs that are less dependent on friction, it's far more effective at transfer. Again, the code is all online, the videos are online, and I know I'm way over time, especially with the difficulties. But these videos are on there. Again, he's not going to win any races. But it was interesting for us to see that we can do this in a completely zero-shot manner by, again, not sexy, but making the simulator as realistic as possible. And we're working on other directions for mitigating domain shift. Another thing that I just wanted to plug, and I'm over time, is what we started, the AI Driving Olympics, which among other things is explicitly looking at sim to real transfer in the case of embodied tasks. So self-driving with these, arguably toyish ducky bots. So we started this competition. I think there've been 6 of them at NeurIPS and ICRA, where there's a pretty high fidelity simulator, but not a perfect simulator. And we can look at how well policies trained in simulation can transfer to the real world. Okay, so just acknowledging my collaborators. And with that, this famous Monty Python skit that I always, Ministry of Silly Walks. All the code, again, is available on our lab's website and CHIP's website. So please feel free to use this. So thank you very much.
All right, thank you, Matt, for the very interesting talk. I think we'll skip questions for the sake of time, but and so just for everyone to know, we're running, maybe I think 15 minutes behind schedule, but we'll just have a slightly shorter panel. But yeah, if that creates a logistical problem for anyone, then just let me know. Yeah, so next we'll have Joanne talk about how lower fidelity simulation could lead to higher sim-to-real transfer.
So hi guys, my name is Joanne. I'm a PhD student at Georgia Tech, and my paper is called Rethinking Sensorial. Lower fidelity simulation leads to higher sensorial transfer and navigation, and this is work done with collaborators at Meta AI. So in the last few years, we've seen a lot of investments in the development of new simulators, 3D scans and assets for data sets, and also techniques to reduce the sensorial gap. But the problem is that no simulator is a perfect replica of reality. And so the default hypothesis in sensorial is that increasing the simulator fidelity will reduce the sensorial gap. However, in my work, we're trying to challenge that assumption, and we're raising the question of, can sensorial transfer be improved by decreasing simulation fidelity? And in our work, we show that that is true. So we study this for the task of point goal navigation. So the robot is initialized in a novel environment. It has to navigate from a starting location to a goal location. The robot has access to an egocentric depth camera and also a GPS and compass sensor to tell it where it needs to head to. And the robot doesn't have access to maps in this environment. And we study this for legged robots. So what we do is we train two different navigation policies, one that uses kinematic physics and one that uses dynamic physics, and we compare the sensorial gap between the two. So in kinematic physics, what happens is that we have a high-level policy that outputs center of mass linear and angular velocities, and then we do kinematic control and simulation. So we simply just teleport the robot to its next state using Euler integration from the velocities that it was commanded. If that resulting state would end up in a collision, the robot is just kept in place. And on the other hand, dynamic physics, we have rigid body mechanics, and so we simulate contact dynamics at every step. So from the same linear and angular velocities from the high-level policy, we simulate the robot step at 240 Hertz, and that's how we actuate the robot in simulation. In the real world, we evaluated across 5 episodes with 3 seats each, for a total of 15 episodes per policy. And the environment is a real-world lobby environment. It consists of realistic clutter like tables, chairs, and things like that. And what we find is that the kinematic policy, when we test it in the real world, we achieve 100% success rate across policies trained in both the habitat simulator and the iGibson simulator. And on average, it takes around 26 actions to get to the goal. In contrast, the dynamic policy, the success rate is around 40 to 67%, depending on the simulator that it was trained on. And the number of actions it takes is over 100 in order to get to the goal successfully. And so in our experiments, we study this across 3 different robots. We do Spot, A1, and Alien Go. We study this for 2 simulators, so Habitat and iGibson, and again, the 2 physics fidelities, kinematic and dynamic. And so we first investigate how large the sim gap is, and we find that it's high for dynamic policies and low for kinematic policies. So what we do is we train policies at 2 levels of physics fidelity, so again, kinematic and dynamic. We evaluate them again in 2 levels of physics fidelities, kinematic and dynamic, across the 2 simulators and across the 3 robots. Alien Go, Spot, and A1. And so what we find is that the policies trained kinematically, so everything on the left side, it results in higher success rate, and policies trained dynamically, so everything on the right side. And even when the kinematic policies are evaluated dynamically, so this is added distribution for the kinematic policies, it still outperforms the policies that are trained dynamically. And we find that the kinematic policies perform better than the dynamic ones because of the scale at which it was allowed to learn from. So here we show that we train both the kinematic, so the blue line, and the dynamic policies, kinematic to convergence. Kinematic policies are trained for 3 days, versus dynamic policies are trained for 7 days, so it's trained for longer. And when we evaluate them both in the dynamic environment, the kinematic policies have a 12% higher success rate than the dynamic policies. And again, this is comparing the walk clock time between the 2. But if you look at the number of steps of experience that the policies are able to learn from, we find that the kinematic policies are able to learn from 10 times more experience because kinematic simulation is a lot faster than dynamic simulation. So being able to simulate faster leads to more experience, which is better for reinforcement learning policies to learn from. So the key insights and contributions are that higher fidelity simulation doesn't necessarily lead to higher sensorial transfer and navigation. Using low fidelity simulation enables faster simulation, which results in more experience and ends up being more robust to dynamics. And another benefit is that you don't need to implement these low-level controllers in simulation anymore, so it saves the developer time. You don't need to tune any gains or any parameters in the simulator. And that the dynamic policies, when you train them in one simulator, it sort of overfits to that controller, that simulator, and it doesn't generalize to the real world. And so we should look into investigating into simulation speed and not necessarily physics fidelity. And very quickly, some other things is that we do assume a black box controller on hardware. For example, we're using the manufacturer to provide a controller from spot convulsive dynamics, and that this might not be suitable for all tasks. So if you are interested in the low-level control for dexterous manipulation or low-level locomotion, then this might not be used for you, but this is useful for action spaces such as navigation or rearrangement. Thank you.
All right, thank you for the excellent presentation, Joanne. Now we'll go into some invited speakers. So the next presenter is Sharon Song. She's a professor at Columbia University, where she directs the Columbia Artificial Intelligence and Robotics Lab. And today she'll be telling us about some of her recent work.
Cool. This works. Okay. Hello, everyone. Thank you for coming. And I hope that people can hear me on Zoom, right? I don't need to unmute myself, right? Okay. Okay, cool. Okay, then I'm going to talk about dynamic manipulation from imperfect simulators. But just before I start my talk, I want to clarify that I think that we are definitely not satisfied with the current performance and accuracy for today's simulator. And my talk is definitely not saying that we should just stay at where we are, but instead, I think what we try to say is that if we have an imperfect simulator, what we can do today to make dynamic manipulation or very challenging manipulation task work. Okay, so in my talk today, my plan is to talk about what do I mean by dynamic manipulation and why it is hard, especially in the context of sim to real transfer, and some of our idea of how to address those challenges. Okay, so what is dynamic manipulation? I think I typically find it's the easiest to understand the difference by kind of contrasting with quasi-static manipulation, right? So in quasi-static manipulation, what we really trying to do is try to avoid or minimize the effect of task dynamics by using very slow movement, right? So today, most of the manipulation system that you see is probably following this quasi-static assumptions. So the good thing is that the planner can assume that everything stops as soon as the robot stops. And that also makes the planning problem easier because the planner kind of can ignore all the physical properties of the objects and just kind of analyzing the geometry of the object. In the contrast, I think dynamic manipulation is really trying to leverage or make use of those system dynamics in order to manipulate objects, right? In other words, it's trying to use the force of acceleration to achieve certain goal. And good examples of dynamic manipulation is actually tossing. So what we do is that we can accelerate the object with the force of acceleration to a certain velocity so that the object will still move after you release the object, right? So, and actually, if you use this kind of dynamic manipulation properly, it actually can drastically increase your system's efficiency and the effective reach range. Right? So for tossing as an example, it's more effective, more efficient compared to your typical pick and place system, and it's also able to place the object into very far away locations by using the acceleration of the force. So that's kind of the motivation why we really care about dynamic manipulation. And I think especially in the context of deformable object manipulation, actually the advantage is even bigger, right? So if you think about deformable objects, one challenge is actually how to, or like in general, under actuated system, is actually how to control those out of contact positions, right? So if you have a cross, how to, the robot actually does not directly have the control over the region that is not directly contact with the gripper. But by controlling the force of acceleration, the system will actually now have an opportunity to manipulate those out of contact positions. So the video is not playing, but basically here are two examples. One is trying to fling a class and the other is trying to swing a rope, right? In those kind of two examples, the system can control those out of contact position, like the tip of the rope, without directly contacting those locations. So those are the advantage of dynamic manipulation in the context of deformable objects. And that's why we really want to enable this capability. So here are two example tasks that we'll talk about and show in this talk, which is swinging a rope to hit a target location. The other is trying to swing a class into precisely into a target configuration. So in both cases, the target goal is defined by key point locations, either by the tip of the whip or the corners or the edges on the class. Okay, so that's the task. And now I'm going to talk about why I think it is such a challenging task in the context of sim-to-real adaptation. So first, because we use this kind of dynamic manipulation, therefore we no longer can ignore the object's physical properties, right? We are now doing high-level pick-and-place planning. The action really need to understand the physical properties of the object. And on the other hand, for deformable objects, the parameter or the physical parameter for those objects is actually notoriously hard to model or estimate, right? And often also in many cases, the simulator just simply does not model certain dynamics, and therefore making like the whole like system identification or parameter estimation particularly challenging. And what makes things even worse is that for both tasks we consider, it actually requires very high precisions to really achieve the goal, right? So in our task, we kind of assume that it needs to achieve under a few centimeter error in order to consider as a success. And here is just an example to really illustrate the big sim-to-real gap for this particular task, right? So in this visualization, I'm showing you the robots swing a rope both in simulation and the real world. So they're actually, the robot is using the same action on exactly the same rope that we actually measure the parameter of the rope, but you can observe a very drastically different trajectory, which really highlights the sim-to-real gap. And then before I talk about our method on how to address this sim-to-real gap, I want to kind of just high-levelly kind of quickly go over why some of the typical methods that we see today cannot really be applied for this problem. So first, I think clearly learning the forward dynamics for this particular problem is not going to work because the forward dynamics in simulation and real world is just so different, right? Learning the model, the full model in simulation, just not going to be directly transferable to the real world. And then how about system identification, right? Can we just estimate the row parameter and then update the simulator, like kind of do this sim to real and real to sim and real kind of adaptation? The problem is that it's going to be very challenging, right? So as I said earlier, because for deformable objects, there are so many estimates, so many parameters to estimate, and many of them are very hard to estimate. And also even more challenging is that a lot of parameters just not modeled by your simulator, right? So here at least the one example is aerodynamics, and there are actually many more, like a stiffness or non-uniform density that's many of the simulators just choose to ignore or does not model. And finally, how about domain randomization, right? I think that's another very popular method to kind of try to address sim-to-real gap. Basically, the idea is that we make the policy, we train on many, many different environments. So in the end, the policy is invariant to all those parameters. Well, the unfortunate part is that it's not going to work for our task because in particular for dynamic manipulation, the policy really need to kind of infer the correct action conditioned on the physical parameters of the object instead of just simply ignore it, right? So as a result, domain randomization is not going to work in this problem. So if all this method cannot work, then what should we do? I think now is probably like a good time to kind of take a step back and think about how we as a human perform this task, right? So actually, in fact, this task is even hard for human, right? So actually, given an unknown rope, and it's very unlikely a person can just hit the goal within the first trial. But the good thing is that we are typically able to get closer and closer to the goal after a few trials. Right, so in this process, what we really rely on, I think, is kind of an intuition about how we can adjust our action in order to affect the trajectory. Right, so what we know is that if we swing harder, the rope will go higher. Right, so although we don't know exactly by how much, but we know the general direction. And what we do is that we kind of rely on this kind of intuition about these adjustments in action in order to adjust our the next actions in order to get closer and closer to the goal. So that is our observation. Basically, the knowledge about adjustment or the delta is much easier to learn and also potentially more transferable to different objects. And then in this work, we try to distill this observation into an algorithm called iterative residual policy. So here is how this algorithm works. So at its core, it's trying to learn a delta dynamics model that's taking the observation of the current rope trajectory and a delta action as the input, and it will try to predict the updated trajectory after you apply this delta action. And then when you execute this, when you use this delta dynamics model to do planning, what you basically do is try to sample a collection of delta actions. You try to predict the updated trajectory and then select the action that will get closer to the goal as the next iteration, or as the next action. And then the system will iteratively do this planning in order to get closer and closer to the goal. So here, just to remind you again, this delta dynamics model is actually trained purely in simulation, which is kind of, as you can see, is quite far from the real world dynamics. But our hope is that this learned delta dynamics model is able to adapt or kind of invariant to different object physical properties, and as a result, is able to adapt to real world as well. So here is a system in action in the real world. So for every iteration, we actually track the rope's tip trajectory using a calibrated camera. And then we measure the shortest distance from the whole trajectory towards the goal as the error measurement. And then at each iteration, we'll sample a collection of delta actions and then predict their updated trajectory. And then we'll select the delta action that give us the closest distance to the goal as the next for the next iteration. And for this task, typically the system will take less than 10 steps to converge. So that's for the system running for one rope. And in our experiment or in our paper, we're actually trying to kind of systematically test how this model, this one model training simulation is able to generalize across many different ropes with different physical parameters. So again, the experiment I'm going to show you will be test on the same model training simulation. So before I show you some of the results, I want to kind of just highlight the difference between the different rope dynamics. Right, so here I'm actually showing you all the trajectories of the rope under the same robot action. And you can see that in the second example, it's actually not really a rope, it's just a very long piece of cloth that has much higher air resistance. And in the third example, it's actually a bullwhip that is much stiffer than the rest of the ropes. And also it has non-uniform linear density. And then both properties are actually clearly not modeled in our simulation, and therefore it's not captured in our training data. So it's really required the system to adapt to different rope parameters based on the real world observations. So here is, I'm going to show you the result trajectory after the policy converges on the same goal. So you can really observe the system trying to take different actions for different ropes in order to achieve the same goal, in order to accommodate different rope dynamics. And in our paper, we actually shows a lot more experiment that's really trying to test the different dimensions of how well the learned delta dynamics can generalize. Right? So we actually test the same model on different interpolation tasks on the rope parameter. We also test with extrapolation, and even for new robot embodiment. Right? So here we basically just change the length of robot's last link, which basically change all the mappings between action and its effects, and really require the system to adapt online. And we're actually pretty surprised by how well the system can, like one model can generalize to all different parameters. So we actually try to stress test the system by kind of interrupt the whole process in the middle and tying a few knots on the rope and see how the system is able to quickly adapt for this kind of unexpected online interruptions. So as you can see that right after the interruption, the error goes up, but after 1 or 2 steps, the system is able to quickly adapt to this new system dynamics and able to regain good performance. And apart from just testing how well one model can generalize to different physical properties of objects, we also want to test how well the system or the framework is able to generalize to different tasks. Right? So here we want to test the same method, which is the IRP framework, on a different task, which is a class placement task with minimal modifications. And I guess long story short, the model will still work. But the only thing that we need to change is that instead of, for the delta dynamics model, instead of taking in one trajectory as the input and predict updated trajectory, now we need to actually input 9 different trajectories, each one corresponding to one key point location. And the algorithm work. And for this task, it actually converges even faster within 3 interaction steps typically. Okay, so that's for the iterative residual policy. And I think the takeaway is that it is really a general framework that is applicable to many repeatable tasks with complex dynamics. Right, so I think the lessons we learned there is that instead of trying to learn the full dynamics model that maps action from trajectory, it's much better if we learn the delta dynamics model that learns to map the changes in action, resulting in how you're going to change the trajectory. And we also show that this kind of delta dynamics model is able to kind of really generalize to many different physical properties in terms of objects and also robot embodiments. And now I want to kind of just take a step back, and then if we look at the whole IRP project, another way to summarize it is actually we basically learned a delta dynamics model from this very imperfect simulator, which shows a big sim to real gap. And I think this idea of how to distill relevant knowledge from a very inaccurate or imperfect simulator is actually applicable for a wide range of systems or like applications that involve complex dynamics that's typically hard to model or simulate. And I think another very exciting way to think about it is that now we maybe open doors to those novel robot hardware that we typically maybe traditionally think that is impractical to model. And a quick example for those kind of systems is actually error-based manipulation. So here we can actually ask the system to learn how to manipulate deformable objects by actively controlling an active stream of errors. Just to highlight that both in this kind of system, both the error dynamics and the deformable objects are extremely hard to simulate, right? It's going to be really, really expensive to simulate them very precisely. So what we did is we actually drastically tried to simplify the simulation process by just using very simple particle-based simulator. So clearly, this simulator is incorrect or like inaccurate, but the system is able to learn a closed-loop policy from the simulator, and basically by learning how to adjust this action based on the visual feedbacks. Right? So the idea here is that although the physical process, like the dynamical process is quite complex, in the end, the policy is actually maybe very simple, right? How to adjust your action based on the visual feedbacks. You just kind of blow on the direction that the class is still not fully unfolded. So as a result, we can leverage this kind of imperfect simulator to do this very complicated manipulation. And in the end of the training, the system is actually able to kind of unfold a large variety of class. So here is actually just a demonstration of a very long dress that is typically very challenging for our earlier work, Flingbot. And this dexterity work is able to like effortlessly unfold those class with error. And of course, there's many more applications. If you start to like think about using error as a modality for manipulation, you can open a bag with air or blowing leaves into a target area. And actually both of them kind of demonstrate the idea that the end policy is actually much simpler than trying to model the complicated dynamics. Right? So for bag, you can use Bernoulli effect to open it. And for the leaf blowing, it's actually kind of just blow towards the general right direction. Okay, so let me try to summarize my today's talk. I think I really hope that today's talk can encourage us to rethink about the way that we model dynamics, or what's the requirement we want to put on our simulator, right? So maybe for many tasks, a perfectly accurate simulator may not always be necessary. So instead, what we can think about is how we can best distill relevant knowledge from an inaccurate or imperfect simulator. And then when we actually deploy the system, when we're training the policy, maybe we can use the visual feedbacks to close the sim to real gap by adjusting the action based on the real world visual observations. And then I think finally, by removing the need of using a very precise or requiring to have a very precise model, we could potentially open doors for many non-traditional robot hardwares and enable new robot capabilities, such as soft robots or manipulating with errors. And I think all those are very exciting future directions. And that's the end of my talk. Thank you.
All right, thank you for the great talk, Sean. Does anyone have a quick question about that talk?
It's okay. If you have a question, let me know.
Okay, great. So, yeah, thank you, Sean. Our next speaker will be Jaemin Hwangbo. So he is a professor at KAIST and an expert in legged robotics, and he'll be telling us about some of his recent work and joining via Zoom.
Can you hear me well? How's my connection? Can someone respond?
Yep, we can hear you.
Okay, yeah, very good. Yeah, I'm sorry that I couldn't attend the conference in person. I had a exam to give here. Yeah, so let me start right away. Yeah, so so today I'm going to talk about some of the legged robotics work that we do here at KAIST. So we mainly focus on legged robotics, and our goal is really to make a system like this run and work very efficiently and very robustly in the real world. And you probably know that learning-based control, especially reinforcement learning, has been making a good progress in this field. There are many papers, now there are like tons of papers that use reinforcement learning to control systems like this. And by the way, these are like all reinforcement learning based sim to real transfer of control policies. Yeah, so today I'm going to talk briefly about the simulation that I'm building and some of the learning-based control approaches that we are working on at KAIST. By the way, so I'm also a developer of this physics simulation. It's called RISIM. So this is a physics engine that I developed during my PhD to use it for reinforcement learning. We use this simulation a lot. There are many other people using it around the world. So here, for example, this policy, so I wrote 8 minutes, but now this policy can be trained in 50 seconds. So you press start, in 50 seconds, you get a running policy. And that's how fast it is and how, so this is, I also like optimize the reinforcement learning framework so that yeah, everything is running very smooth. But this is a general physics simulation, so you can use it for other purposes as well. So compare it to other physics engines. So our physics engine is hard contact simulation, which means we don't allow penetration. On the right, you have a soft contact simulation where you see the feet going into the ground. So I'm not sure if the video is playing well, but the feet are going into the ground. On the left, we have hard contact simulation, which doesn't allow penetration. So it looks more realistic. And we are also building realistic, visually realistic simulation as well using Unreal. We can also download it from riseteam.com. And there are also people around the world using RISE-Team to do various research work, and also there are many companies buying this now for their products. Yeah, so that was advertisement on RISE-Team. So we'll jump into some of the research work that we do here at KAIST. So the first work that I want to introduce is learning-based state estimation. So if you're not familiar with legged robotics, we need good state estimation to do proper control. And the way we did the state estimation is more traditional approach. We've been using an algorithm, a mathematical approach, and to figure out the state. And the core of this mathematical algorithm is assuming that the contact point doesn't slip. If it doesn't slip, then we can use the fact that the contact velocity is 0, and we can narrow the state estimation. So we can decrease the covariance of the state estimation so that we can get more accurate information about the state. But this kind of approach doesn't work if you have a deformable ground. So for example, if you have a legged robot running on soft sand, the feed will go into the ground, and there is a violation of this constraint that the velocity is 0, right? So we need a better approach to handle this contact scenario. And what we are proposing here is that we actually embed this state estimation learning inside this learning framework. So while we are doing reinforcement learning for the policy, we use the same sample to train a state estimation network. The state estimation network is quite simple. This is a common MLP, which takes the sensor measurement as an input and outputs a set of states, such as the body velocity, the foot height, and contact state, and so on. And this is fed to the policy network. And the whole thing is just trained at once. So we are not making new samples. We just we reuse the samples from reinforcement learning to train this estimation. And what surprised us is that just this relatively simple approach where we do concurrently train the state estimation has very good performance. The without estimation is very common approach where we do student-teacher approach to figure out the state. Using well, we don't explicitly represent the state. Here we learn the state in a form of latent vector. Let me correct this. So that point is implicit, where we don't have an explicit representation of the state estimation. Implicit is where we learn it as a latent representation. Without estimator is just learning the whole policy in an MLP. And sequential is learning the state estimation first, then learn the control policy. And you can see that among the 4, we have the best performance on top. Here we have very close performance. And so if I go directly jump to the video, we have using this state estimation, we could make the robot run very fast. So before this publication, the record for Minchita running was 2.4 outdoor, 2.4 meter per second outdoor. We reached 3.75 meter per second outdoor. And we also, our strength is that we can handle the slippery condition very well. So this is a default controller, default state estimation from MIT. As you see, this will fail because this uses an assumption that the contact point doesn't slip. And on the contrary, if we learn the state estimation, and we can do this. So here we commanded the robot to stop in the middle, and you see that it can handle the slipping condition very well. And you will see that the feet actually slip a lot, and it's important to do proper state estimation in this kind of situation. Next topic I want to talk about is the local planner. So the traditional control approach, control framework looks like this, where we have a mapping global planner, such as RLT, and we have a local planner. So given this rough plan from RLT, where should I go? Exactly how, what trajectory should I follow? And then that path is passed to the controller. And we mainly work here And the environment looks like this. So we have very cluttered environment. We have many obstacles, and we consider a contact with the environment failure, right? So the robot has to figure out this quite complex trajectory where it doesn't make any collision with the environment. And this is a very challenging problem. And traditionally, this was done using a waypoint-based method. So it draws a circle around it and find the intersection of the global plane with the circle, and just make the robot go directly to the obstacle. And you see that this will just make it collide with the obstacle in this naive approach. There were a few learning-based approaches previously, but they are reactive policies, which means you cannot plan for a long horizon. So we wanted to do something better. We wanted to have a collision-free trajectory while handling over long horizon. And the approach we did is by training a command sampler and learning the model of the system. So actually, the learning this model is quite complex because we have complex collision geometry, but we could train this forward dynamics model, which evaluates the collision probabilities and the trajectory. And of course, for that, we need a command. If you have a sequence of command, we have a fixed dynamics, really collide with the map. So that's what it's doing. And the informed sampler is selecting good set of trajectories. So if we just sample random trajectories, this will take very long time to evaluate, because the trajectory that we want is quite is very unlikely to be sampled in a random sampler. So we train this informed sampler using conditional variation autoencoder, and this will make many candidates. And then we evaluate that through the dynamics model. Then we figure out the best trajectory. And using this learned dynamics, we could have the high accuracy. So here you will see that the FDM, the trained model, is having less error than the approximate model, such as a sphere and boxes. And it also has a lower computation time. So our approach is more efficient, computation is more efficient and more accurate at the same time. And if we look at the success rate, the SR, so if you focus on this column, which represents the hardest task, and ours has about double the success rate over the PD controller and much higher than the other approaches. Yeah, so it's really important to have this mixed sampler and the dynamics model. Yeah, so here you see very complex geometry where this planned, the local planner is handling. So on the right, you see that also works quite well, but sometimes it fails. And because we just consider the collision of failure, this has a very low success rate. And we can also just introduce new objects in the middle. So this green object is just was unseen, and it can be handled by the sampler. Because we are sampling the new trajectories every time, it can just handle unexpected obstacles. Yeah, and so we tested this on multiple environments, and you can read more about this in this paper. Okay, and another topic I want to introduce is running on these complex terrains. So we want to make the robot run on this kind of environment. And we were thinking about the most difficult environment for Legi robots, and we figured out that this could be it. Because this very soft, when running on this very soft sand, the feet will be buried in the ground, and the robot is basically swimming in the sand. So this is completely different dynamics. Using a typical rigid body dynamics like RISIM cannot handle this properly because it's a rigid body simulation. So that's why it's a complex system. And before we get into that, we just want to talk about this robot rival. So we built this in our lab. It's a Lego robot, 12 degrees of freedom, 26 kilogram. You can think that it's about the size of alien ball. I think that's the closest match. But yeah, we built this in-house. And for handling sand, we have to build a realistic sand model. Here we have to handle this added mass effect. So if the feed penetrates into the sand is packing, and it feels like the feed is heavier. So we have to handle that. And we also have to handle the friction. We also have to handle the resistive force as the feed move across the sand. So if we build this proper model and introduce a paper, which will be published very soon, but it's still under embargo. And using our model, sorry about this. So using this model, we could simulate various types of sand, as you see here. And it's actually not so important to simulate exact sand because as long as the reinforcement learning can experience all types of sand. And yeah, if we jump directly to the video, so that's the result. Yeah, we could make, using this approach, we could make the robot run at 3 meters per second. And I haven't seen any Lego robot running at this level of speed. Yeah, we could, it was very robust. So we tested this multiple times on beach, and we didn't see it. Yeah, using our approach, we didn't see any failure. So this is very robust running on sand at high speed. And it's not only just for, it's not only for sand, because we are modeling the sand, we are modeling the parameterized sand, so we can simulate a very hard sand and very soft sand at the same time. So this can transfer to soft matrix, grass, and running track, and so on. The policy is, as it experiences the terrain, it adapts to the terrain so that it can generalize to different types of terrain. Yeah, so that's all for my talk. I'll be happy to answer your questions. Maybe I'm over time. Sorry about this.
All right, thank you, Jimin, for the great talk. Are there any questions? So I might ask one quick question about the work on running on sand. So are you doing any sort of explicit or implicit state estimation when it comes to the properties or parameters of the sand deformation?
Oh yeah, so that's a very good question. So some of that slide is not here, but we have an encoder that sees the sand sensor observation and tries to map that to the sand properties. We have this explicit state estimation. So we have two encoders. So one is this explicit state estimation, which outputs the exact body linear velocity, contact state, and so on. And there is another encoder that encodes the sand properties. Did that answer your question?
Yeah, thank you. All right, so I think that concludes all of the speakers for our workshop. So now we'll move into the panel section. So panelists and speakers, maybe we can set up some chairs at the front of the room. And well, yeah. So I mean, I think definitely we can welcome questions from the audience, but I also have some written down to maybe start some conversation. So I guess the first question that I have in mind is sort of so domain randomization is sort of a key component in a lot of sim-trial systems. And I think that today people have espoused lots of different ways that we can potentially use some sort of estimation, whether it's like implicit or explicit, to try to make systems adapt to that randomization rather than just being robust to it. So I guess the question I have is sort of, is there a benefit of doing state estimation explicitly over implicitly? That is maybe in more of like the RMA style, or do we need to enforce it at all? Could it just be learned by our policies? I think, yeah, does anyone? Okay, maybe do you want to start with the?
Sure, I think, I think what is important is to estimate the parameters so that, we know what domain we are in, so we can tune the policy to that domain. I think the question of whether we need to do it explicitly or implicitly, I think the jury is not out there. I think, there are some works like the RMA work which do it implicitly. There is some work like Jemin's work which do it explicitly. But I think the heads-on comparison hasn't really been made, right, in a rigorous way. So, I would love to see that comparison, in some future work.
Yeah, I think maybe I can add on that. I think your question has two parts. Like the first part is kind of like about domain randomization. I think we kind of all see that it has its limits because domain randomization is kind of really trying to make the policy invariant to certain properties. I think that only work for like certain scenarios, like you probably want your system or policy invariant to lighting, but there's a lot of things like a lot of manipulation or locomotion system actually need to be sensitive and the condition adapt to those like aware of those parameters instead of just ignoring them. So I think domain randomization kind of already kind of gets to a certain limits. I think there's a lot of need to be done that kind of either implicit or explicit model the state or model the environment so that the policy can be more aware of those different parameters.
So to follow on that, I just want to stir the controversial part of things. So the reason we want adaptation instead of pure domain randomization because we feel that it's a trade-off between optimality and the robustness. But my question is, if we have a big enough capacity in the neural network, is it possible that domain randomization will still work really well for all the physical parameters to increase the capacity of the network? I don't know, but it's just one thought. Maybe it's just a temporary solution that because we don't have the capacity in the network, because we don't know how to collect enough data to feed that large capacity model. So we have to do this implicit or explicit domain adaptation.
Maybe we're also not robust enough to optimize the very high capacity model. It does I think what you're saying is a big enough model will estimate the domain implicitly, right? Because that's just optimal behavior. So if we optimize it right, that's what it should be. I think maybe the failure point is the lack of an algorithm that does the optimization well, especially in CoRL. It's often still a problem, but otherwise, I would agree with you.
Yeah, just to add to it, right? I mean, maybe that's what has happened because if you see all these work, we have been using supervised learning, like to do both explicit or implicit optimization. Right? So in some ways, I think doing this at RL still seems to be challenging. With supervised learning, it seems more possible.
Following up on that question, I wonder if there's also an advantage to that estimation. So basically, a lot of people do what in the example. On that concept, where
Just if you understand.
So So is the question that, in some of the works, the contact points are predetermined, and if we are working in scenarios where we can't predetermine the contact points, what needs to happen?
Yeah, I guess what I'm, sorry, it was not so much a question, as I guess also a comment on whole body contacts, unknown contact, basically really make contact, making and breaking contact, make state estimation, explicit state estimation, really important. And maybe that's where this is. Because we want to need explicit state estimation.
Actually, I'm a big fan of implicit state estimation. I feel that's just like really liberating about like what kind of parameter that you need to model, what kind of like whether you model context or you model something else. And I feel like giving the flexibility for the model to determine like whether what kind of combination of latent representation I need feels like very powerful. And if we have the right model, like it feels like I can learn also the right stuff. Yeah. Yes.
Yeah, Jimin, I wonder if you have any input as someone who has had some good empirical success with explicit state estimation in your work.
Can you hear me?
Yes, we can hear you.
Okay, good. So, I think the difference is if the reinforcement learning has to figure out what it has to learn. So there are like there is a part where it has to learn what it has to like the type of the latent vector. So how it should look like and what it should be conditioned on. So that's one part. And then it has to learn to figure out how to map that from the sensor information. So the explicit mapping is good in the sense that we are giving the network that this variable is important. This state is important for the control. And then it's much easier to learn. But then also that takes the intuition from the engineer. And if you're familiar with the system, then you know what state information that the policy needs. Then explicit state estimation is a good approach. If figuring out what state is important takes very long time, then maybe you can do it implicit way. But from our experience, if you know the state, so if you know which state is important, then explicit state estimation works better.
Maybe I want to add on a few things. So first of all, I think when I answer the question, I confused two things. One is state estimation, one is system identification. So my answer is more on the system identification for like domain adaptation. Now, if we are talking about state estimation, where you use sensor data to figure out all the states, I think explicit state estimation is very important. One reason is if you are doing the training in the real world, what you need is like how far the robot has moved. So that is not some sensor data you can get easily. So explicit state estimation feed you that information. So that's very important for at least the real world training.
But in the past, is thinking of the house, it doesn't matter how has moved.
Yeah, it really task dependent, right? If we are talking about like a locomotion, or if we are talking about some manipulation task, you want to know whether the object you are manipulating has rotated into the angle that you want, then state estimation help you to get the reward function. So that's essential if you want to train.
That's a different question. I mean that because that's not what the robot needs. That doesn't mean that. So yes, to provide the supervision signal, provide the reward we need. Yes, that doesn't mean that we have to follow explicitly control.
Honestly, that's not the condition on most estimates. I do feel like there is like a kind of a difference on like modeling the robot itself and modeling the external world. I think in Locomotion, I think there are some like modeling for the external world, but most of it actually is modeling the robot dynamics. Right? So in that case, I think explicit model will probably work really well because we do have a pretty good model of the robot itself. And if you can model the context, that's the external things that you want to compensate. But if you think about modeling the external world, come with a vision background, then you kind of really feel it's really hard to do explicit state estimation, like modeling object pose, and there are so many things that cannot be described by pose. So I think there will be a limit for explicit state estimation.
Yeah, so maybe if we go 10 years in the future, we will look back and say, hey, in 2021, we look back at AlexNet and say, hey, we should just learn features, right? So maybe 10 years from now, we'll look back and say, hey, maybe we should just do it all implicitly and not do anything implicitly.
Next year.
Next year.
But in the end, the answer is probably just that it's an inductive bias. That the system that inductive bias is the right one. It will make learning a lot easier, and it will make the system generalize better. And when it's not the right one, it will not necessarily reduce it. It reduces the flexibility of the system.
So maybe picking up on maybe a more controversial topic, right? So do we think simulation is a crutch in a way that in 10 years from now? I think this is a question which Gabe came up with some time back. In 10 years from now, what do you expect? Is most of the data going to come from simulation? Is it going to be from the real world? Or is it going to be a mix of both of them? So is simulation a short-term answer that we don't have algorithms that can collect data in the real world, so therefore we are doing simulation, and maybe we'll solve it, and 10 years from now everyone will do real-world robot learning? Curious to hear what people think.
I think we don't know yet. I feel both technologies are moving more fast at the moment. Currently, my guess is it's going to be a mix of the two for various reasons, but I think we just don't really know yet because I think we haven't pushed either to the limit.
So just to push on a binary answer.
Maybe I have to bet. Only one.
Yeah, so suppose someone told you, I'm going to give you $10 million, $100 million. You build your team, but you can only do one of these. You can't do both. What would you make your money on?
It's very hard. Yeah. I will bet on simulation. Again, it's not a black and white binary answer. I think it will be mixed, but I still think that even in 10 or 20 years, simulation data still have a great value. If you just look at the autonomous driving car, community, they have a lot of data, real data. There's so many Tesla cars running every day. They have more data than they can even consume today. But still, that the simulation plays a very important role in self-driving cars. So if you extrapolate that, and there's an analogy game for robotics, I don't think in 10 years every family is going to have a robot. So we're not even there yet. So I think simulation data is important.
So what ask a question? Yeah. That topic. What tasks do you see with these algorithms? Like the simulations are going to be very, very different. The things that we're trying to do are going to be much, much more complex. Whether or not we can simulate those things is going to be different. What do you think the next challenges are going to be?
What the last question? Thank you for your question. I actually think it's representation that what actually but if I was putting my money on something, I think it would be
very specific.
I think what we will not have is
So maybe picking up on your question of, what we think, could be done in the 5 to 10 years, I am pretty optimistic about things that involve rigid bodies, right? And if I don't have soft things, I mean, I think you can do a lot with your rigid body, right? I mean, if I walk into my apartment, I'm like, hey, why are things not arranged? I would be very glad, if my living room was completely arranged, if all the dishes went into the dishwasher, right, and someone started the dishwasher, just arranging things in environments, I'm pretty optimistic that we could get there. Now, I think for the soft things, I think there's one belief that people say, hey, we need to build soft simulators first, and we have to make them really well. The other thing which could happen is if we can do rigid tasks first, that will be a very good pre-training for soft things. So maybe even if we have, slow soft simulators, it may open the floodgates because we will know already how to move the hand, how to interact with things. What will be different is a kind of interaction. So I would put my money on rigid body, really making sure we get it right. And then maybe going on the soft bandwagon and see how far we can push it. Or maybe I'm at odds with Shuran.
Yeah, okay, let me argue back. Okay, first is about I think going back to your home example, if you think carefully, I think it's around our environment. Actually, you will find really hard to find an object that is completely rigid, right? Almost nothing. I think, and also
except my plates and the spoon and the bowls.
Okay, but the rest of the stuff, yeah, I think there is a large portion of objects in our environment is not rigid. But even beyond that, I kind of feel personal view, I feel like the idea of if we solve the rigid body and the same method could typically apply to soft body or soft object manipulation. I don't 100% believe that. I kind of feel like maybe really it requires a different way of handling deformable objects. And I think one thing that I think a lot about is state estimation, right? So for rigid body, the word is so simple, we can just use 6 numbers to describe the state. And if you know the geometry, you know everything about this object after the 6th number. But if a deformable object, it's really hard to decide the states. It has infinite degree of freedom. And even for a rigid object, when you have too many of them, become granular media or particles, then those kind of state definitions no longer apply. So I feel yeah, maybe we shouldn't go this route of rigid first and deformable. Maybe we should do parallel at very least, and then think about alternative approach at the same time.
That's why we're in academia, right? We can go see both of them.
Yeah, and also go back to your original question about simulation and real world learning. I had to say that, but I kind of want to bet on simulation, but with a different reason. Is that I kind of feel simulation is a way for us to represent what we understand about the dynamics or the system, right? Or it's actually our representational model, and it can be the simulation can be learned, the simulation can be physics based, but that's actually really represents how well we can model the world. And then if we have an improvement on word modeling, then we can always see an improvement on simulation. And we may not necessarily directly reflect on learning from real world. So yeah, that's my take.
Maybe just to go back on the soft objects thing, right? So one thing you're saying is, hey, we can't really define the state of the soft object in a reasonable way, right? So that creates problem both for training in the real world and training in simulation. And then is your point that people think of a fundamentally different way to tackle those things?
Yeah, that's a good that's a good question. I think there are I have a few ideas, and I think a lot of our work is kind of trying to answer that question. So for example, today in my talk, I'm trying to say that when your simulation is not perfect, can you still learn a reasonable policy that is applicable for real world? And that's actually, I think that doesn't apply for all the possible applications, but in some cases, when the policy is actually simpler than the dynamic process itself, then that's possible. And or when there are certain things that is actually particularly generalized, it can generalize across different physical parameters, or can generalize across simulation to real world, then learning that knowledge is more useful than learning the before dynamics. So there are small examples, but I don't have a good answer for this is the way we should do things.
Isn't soft versus rigid what's much more controller can learn more on how we generate the data. And if one is easier to simulate, maybe one is easier to solve first. Not because the state estimation is hard, because we just use a big neural network to do state estimation anyway. And it's really about creating the training data for the controller. That's how I have understood your approach.
I see. But even for that though, I think like for soft body simulation, we are not too bad. Like we are not, we are we are able to simulate to a certain degree, and there's a lot of developed there. So I don't think that we're not necessarily able to generate similar amount of training data, like compared to simulation, like rigid or deformable. And there are also still a lot of problems need to be solved for like even the rigid ones. So I don't see there's a clear difference.
Isn't there a difference in the speed in which you can generate data? Like rigid body, you can do it very fast, unless there are many rigid bodies, right? Because the same problem with soft things, that most people represent soft things as rigid bodies with strings. And then the problem is you have too many bodies and the simulation becomes really slow.
Yeah, but the speeds, we can let NVIDIA to solve it, right? So, like there is like such a fast development on simulation and on the compute.
So now you're agreeing with me.
Yeah.
So now you're agreeing with me. You're saying that we should solve rigid bodies now and then wait.
No, we don't need to wait.
I just want to have a quick comment on the speed of simulating soft body. It's actually faster than most people imagine. It's just a trade-off between accuracy and the speed. If you want to do full finite element, it's very slow. And you have an linearization, which is faster. At the other end, you have position-based dynamics. There's a lot of graph paper on that. It's like faster than real time, much faster than real time, but you lose this physical accuracy. At the same time, you learn that the physical accuracy is not that valuable if you have the domain randomization. So it's sort of requires you to learn to generalize different physical phenomena. So it's really, you want to run like throughput of simulation and maybe just choose the position-based dynamics for a soft body simulation. That might be one solution.
I mean, I don't know, I take issue with that. I mean, I don't think domain randomization is the answer here. If you look at, again, some of the simulators that I've played with, they're very fast, as you said, but they're ridiculously inaccurate. I don't think domain randomization is going to solve that. And an issue might be, as I discussed earlier, okay, we make our capacity of our network sufficiently large that we can capture everything. And that sort of is the solution. And we have this distribution and simulation here, distribution and reality over here. And what's the thing? What am I going to do? I'm going to add noise and broaden this distribution as much as possible. Well, that means we're wasting a lot of effort focusing on things in this domain that are very far from physically realizable. To me, that doesn't seem like the right answer, and it's not obvious to me that maybe in some rigid robotic domains, with friction, that's feasible. But for soft body domains, the space is just so far more rich that widening this distribution is not the right answer. We need better solutions, in my view.
Yeah, so I mean, I agree with you in what you're saying. I think maybe let's try to unpack it, and maybe there are two different parts, right? So, the one thing is when we're randomizing things, what do we expect, right? So consider an example that, there are demonstrations of quadrupeds which can go over gravel, right? Which is something we don't end up simulating in simulators, right? You could do it, it's just very slow, right? And the question you might ask is, hey, why can we still walk on gravel when we don't simulate it? Right. So one intuition is, if you think of gravel, what happens? Like if I place a foot on a stone, the stone slips. Right. The stone moves and the foot slips on the stone. There are those two things. But now if I'm in simulation, what if I do is I lower the friction of my domain, but I also apply random forces. So in effect, I'm able to emulate, what gravel is going to do. Right. So I think one bet is that the space of perturbations is low dimensional, but those perturbations can come in many different ways. So if we just get one way of generating those perturbations, maybe that is going to be sufficient, right? So
that's different, though.
Yes.
Again, my understanding of what you're saying is that we have a simulator that. So in this case, you have a simpler simulator. The simulator is not capturing this.
Yes.
So we're going to basically add some domain randomization such that it does.
Yes.
Versus having a simulator that may or may not capture this phenomenon, but captures a lot of other things that don't actually exist.
Yes.
That's not something that we can deal with by adding noise. It's almost like we want to remove noise in some sense.
Yeah. Yeah. Yeah, which is yeah. I mean, I think over there, which is what people were saying, that if you're doing system identification a priori, right? I mean, that would be a good thing. Right?
And better simulator always helps. Like we hope that the simulator is not gonna be better and it's gonna not be that random and it actually get us closer to the real world distribution just by itself. I think that's my hope. I do believe that.
Or maybe there's a representation that does better translate. Less sensitive to image.
I also want to say I agree with you. I'm not saying that we just blindly collect more data in practice simulations. There's always an axis that you can improve on to improve the accuracy of the simulation. But at the same time, we need to understand the trade-off. If you go towards better simulation, it means you put more like a human power to understand the physics and engineering it well. On the other hand, it's like you just collect a lot more data, but maybe it's irrelevant data. You just burn some like CPU cycles. If the CPU power is cheap, human is more expensive, then you know where the trade-off is. There's always this slider you can decide based on how much computational power or how much like brain power you have to dial your where you want to be in that spectrum.
So maybe a question is, what is a problem that you would like to see, which will convince you that maybe the sim to real approach can make meaningful progress?
In soft body or more general?
Generally.
This is a question for everybody.
Yeah. Okay, maybe let me rephrase it, right? And maybe I can just also put it on all of us also, right? So have we, in the last 10 years, replicated what carefully tuned MPC can do? Or have we really pushed the boundary beyond what a carefully tuned MPC controller can do with all the learning research which has happened?
I think that's a good question. I want to hear Jia's answer because you know how to tune MPC very well. So what do you think?
So in my point of view, I think that we have already got beyond MPC level of performance in locomotion, the field I'm more familiar with. So first of all, you see the huge speed up in terms of the progress of the entire community on locomotion. Just from the ETH demo in the early this year, it goes through the trails on a wide variety of terrains. It's very hard to do it in MPC. It's a very carefully tuned MPC probably can do it, but just within like a year, they show this progress. I think we have been like way above the performance MPC for locomotion.
Probably the interesting part is that just integration with research. That's right. That suddenly becomes a lot easier with more or less and the arbitrary abstractions and the status dimension part solve implicitly through some representation testing you have to engineer and it fails.
So to continue that line, I also want to ask kind of, do you think that, so there have been a lot of like recent successes in general, I think, across sort of sim-to-real approaches, and one hypothesis might be that a lot of it was driven by sort of faster simulators that have become available in the past years. So I'm curious, if first, do you think that faster simulators will continue to become available in the coming years? And second, would that lead to continued large increases in performance? Or is there some wall that we're hitting in terms of either like sort of maxing out, computers aren't getting that much faster and we won't develop better methods, or maybe more data wouldn't actually help in these domains anymore because we have, are we hitting other walls, or can we expect the scaling of simulation speed you figure out some progress.
I see a great potential there. I think like every year we see the simulator is improving, and also I think now not only robotics care about simulator, like a lot of people care about it, like metal work care about it. Like there are like so many forces and also like money put in, I do see like there's a great potential of moving forward, and it will be faster, better. But one feature I really hope to see is a simulator that have this knob allow me to tune the speed and accuracy. Because for different type of application, or even just in different stage of training, maybe I really care about different things. Like in the beginning, maybe I care about the speed, but later I probably want to really care about the accuracy. So I really hope that someone can develop this simulator that allow me to tune the knob of like trade-off between the accuracy and speed.
That would be very nice.
Yeah.
So I kind of have a follow-up. Like, what role do you think mixed-fidelity simulators will play? For example, have you guys reached the limit of simulating 11 soccer players per side? You know, maybe you don't care about 11, you just care about the ones that are on court. Do you think that resources and, you know, as you say, you know, a slider, but perhaps a slider in certain ranges, you've got a soft body over here, you know, do you think that this is something that we could invest in the next few years, develop into you have large multi-scale multi-agent things, but also high fidelity work?
I think we always want that, but it's really depends on like whether those like developers where they put their focus in. And I guess your first question, like when you start the question, you're asking about where the mixed reality kind of environments how these simulation. Yeah, I think it's exactly right. When you're thinking about like human-robot interaction or multi-agent interaction, I think those kind of simulations can really
So in the future, we're going to want robots to be able to solve tasks in very rich environments, very wide range of tasks. Simulation kind of for free almost gives us a huge amount of data in a very narrow set of tasks. But as you increase the sort of spread of the tasks and spread of efficiency, that's still
generative model for simulation environment.
Yeah, I mean, go on.
I wasn't trying to say that it's better than in the real world, just to sort of remain expensive. The scaling is kind of linear and complex.
Yeah, maybe, I mean, I like to see it in a different way, that, you know, given the tools that I have, what is the tool which can help me make the most progress right now? It seems like simulations can be more scalable than real world, although, you know, there has been a lot of disagreement already, you know, on that, right? So I just see it, you know, if we had a better way, we would use it, but it seems to be like a way in which we can make more progress. And then maybe as Akshara was pointing out, right, and Ashwaran was pointing out, right, if we have good generative models, maybe we can overcome that problem and go to more diversity.
So I guess where I was what are those sort of what things work better than just having it seems like there's a wide range of possibilities there.
I take it. I guess the question is, what are the ways that we can take the current simulator better? I guess if I summarize it, high level, you can have learning-based simulator that you add a learning module to it. I think generative way is like one way to do that. And the procedural generating, I think that is something that in graphics actually has been studied for a very, very long time, but we haven't really seen it in robotics yet. Like there is actually a lot of rule-based way that we can generate very large-scale environment that kind of looks realistic. We can bring that in. What else?
Yeah, I mean, one way to think about is it's, we have all these fancy images from diffusion models today, right, which look very good. What we don't have is the URDF of those things. Right? So somehow we can link diffusion models to generate the URDF and the scenes together, right? Then potentially we would have, all these rich looking things, but also we will be able to simulate them using those things. So I would, really bet on maybe scaling up, generative models, but also adding in the physics component, which helps them to simulate the physics. I mean, that could be one way.
Yeah, another idea just coming is actually like, if you think about computer vision, what they are doing is actually from images converted to 3D like models, and we can actually use that to scale up like the environment construction. We have a lot of 2D images online, and we can like infer 3D model or even infer URDF from those images. And if that is mature, then actually we have infinite internet scale there.
Maybe this is Nicholas, you were talking about this, right, in your talk. So I'm wondering, what's your opinion? Given that you have, I was just talking, I haven't done.
I think my opinion is that at the moment this is still extremely limited. But I think we need to think about ways, anything to learn more of the simulation and learn probably. I'm undecided whether we have to learn a structured simulation or not, but at the moment this seems like the more, maybe the thing that seems just more likely going to, or where I feel more confident that it will work to some extent. When I say structured, something that has an explicit state that represents the world in the same way as the physics simulation does. Because you could also mention just training big world models. Which has been less explored, I think, than just images. And it's video models, I guess, that will get that will eventually probably be good enough to make certain types of predictions, but that doesn't tell us how the physical system or the physical system.
Maybe there's a question from that, and then we can.
So I guess like generative models mentioning leveraging internet scale data, but I guess like something interesting internet scale data from carries the physical properties, and kind of hard to imagine how do you generate those properties models with some model algorithms. So what is your
I guess that's a question for me. So I think even today, with today's simulator, we kind of need to define those parameters. So how does those parameters come to because someone write it in? And then I guess probably that's just require either you can assign something reasonable in a reasonable range, or you can come estimate those parameters or have an estimate of distribution of those parameters from some other models that serves to, for example, estimate the dynamics, the weights, or the central mass of typical objects based on observation. And so probably that means that there's more work to be done if you want the image to actual 3D environment is physics-based simulatable environment. But I don't think that is completely impossible because in our interactions in environments, when we see an object or when we see an environment, we do have some kind of estimation of it.
But I think that's because you have interactive
yeah, so it means that probably like the simulator probably will also require certain kind of real world interaction data to augment with their internet stuff.
GPT probably knows. You probably ask GPT, oh, this is a chair. What's the dimensions?
Yes.
How much does it weigh? What's the allowance?
But I don't think you can ask GPT where's the center of mass of the bottom of the
yeah, for those parameters, maybe need some. I think probably the easiest way is to run through certain interactions. But probably that means that you need to interact with all the possible objects.
So I have one more question for the panel. So I think a lot of studio works right now is simultaneously propose like a new problem or benchmark and also a solution to that problem, as compared to, for example, if we do optimization or RL in simulators, maybe they'll have some benchmark they're continuously making progress on. And I think there are some real challenges in creating benchmarks into real transfer because it's hard to collect a lot of evaluation data in the real world and get statistical significance on those benchmarks. And B, everyone has different, the diversity of the real world is sort of inherently, it becomes hard to construct a standardized benchmark. So do you think that the field is suffering for lack of standardized benchmarks, or do you think that's a problem at all? Do you think we can continue as we are and we're making progress?
Is that specific to Sim2Real or just robotics?
I mean, I guess it is a kind of a robotics problem in general, but
but I guess robotics. I mean, it applies in the same way to robot learning.
Yeah, I think that's, so do you think that's not a special problem to Sim2Real? It's all robotics that has.
I feel it probably applies to everything, every robotics evaluation in the real world.
I think Sim2Real is hard because the metric is hard to define. So you have the simulation trajectory, you have a real trajectory, what metrics do.
I guess it depends on what you want to benchmark. If you want to benchmark the performance of the system, the final performance of the system, which you can see implicitly as a benchmark for your Sim2Real, then it's just the same problem as I guess evaluating the robotics problem in general. If you want to make more granular inferences, maybe about a certain step of your pipeline, then it's different.
So actually, I think for your particular question, I think today there is a debate over like the benchmark in robotics. I didn't watch it, but I really want to watch it afterwards. Maybe that can answer your question. Like, or I maybe give you some thoughts. I think indeed benchmarking in robotics is first very hard, and maybe a lot of people can argue that is sometimes it's not particularly beneficial because like once you define benchmark, it kind of constrains the creativity of the field because everybody starts to think about the same problem. So I can see both ways. Actually, I really care about I'm curious about other people's thoughts.
Yeah, I mean, I think that in the past years, if you see, there's a lot of standardized hardware which has come out, which was not the case maybe 5 years ago. So we're definitely seeing progress in hardware being consistent across different labs, which I think can drive it. I think I agree with you that there is, something about being able to innovate on different problems, but also different levels of the stack, right? I mean, if we say it's a benchmark, we fix the hardware, but the problem might be a hardware problem. And then we become artificially constrained, in a way. So it seems like, maybe if we run different, levels of the benchmark, where say, hey, you can only do control innovation, or you can do control plus perception, or you can do control perception and hardware, but we're going to just see how well you can solve that task. Maybe it will, help.
But that's not good for end-to-end systems, right? Because it across all the stack.
But then, if, as Nick was saying, that if all we care about is the final performance, right, then maybe it wouldn't really matter. Right? Maybe, right? I mean, maybe that's one way to look at it. I'm not sure if you will agree with that or disagree with that.
But it's still hard to do. In general, it's hard to do. You have to do it. You have to run this thing in the real world. First you have to recreate the same setup that someone else is using, and then have to run it in the real world. Have to run it many times.
So I'm wondering,
independently of defining what the benchmark is in the first instance, right? Because the field is moving relatively fast at the moment, so what is a meaningful problem is changing quite quickly, and typically in different facets. If you think about a real world task, then you have many different facets.
we're trying to think about the different levels of the system. So when we can mention it separately, or when we just benchmark them as one, when you have solved it.
I'm curious on the radical suggestion, like instead of trying to recreate the environment and trying to, evaluate on that, what if we said, there are, 20 people, right? And they can tweak the environment as they want, and then they can let the robot do things, and then they're going to come up with a score of how much they like the robot, right? Because eventually you want to, suppose if we say, we want to put robots in my house, right? Then, if I'm a company, I would care about how satisfied is my customer, right? So if we, instead of trying to make everything consistent, we say, hey, here's a robot, play with it. How satisfied are you? And then we average across people how satisfied they are.
You still need people. All I would say is that to do that, you need to have a consistent evaluation involving, 20 people who all work with that robot. So I think you've just pushed the problems to another level. If you actually want to make it, so you now have 20 humans involved, you need to make sure that somehow that's a matched population every time you run this experiment. So I'm not sure this is the solution. It just makes everything complicated. Because
I also agree that this makes things more complex because of the human involvement. You get all the subjective opinions, all these noise. So I'm also working on social navigation. So the only way to evaluate social navigation, whether a robot is navigating in the appropriate way, is through user studies. You have to go through so many user studies to get anything that have the right signal. And also it is like a cultural group dependent. If you send the same encounter between robots and humans go to India, China, USA, they're completely different. So it's actually making things more complex.
But I want to say that I support that because I feel that's indeed the ultimate goal that we want to evaluate. I think if you want to define one evaluation, it's the satisfaction of the user. But maybe I also agree that it's very complicated, like very hard to actually get an evaluation measure right. That doesn't mean that it's not worth thinking about.
Cool. So I think it's 5:30, so maybe we can conclude the panel, and maybe we can have a round of applause for our panelists and also all of our contributors today for a successful workshop. And yeah, thanks to everyone who attended today. I hope everyone came away with some fun food for thought, and have a good rest of your conference.